And we are live. So, welcome everybody to the fourth day of the Space Renaissance International Fourth World Congress. The first session of today is the space tech and technology and industry, with a lot of high-profile papers to be presented. So the chair of the session is Werner Grandl from Austria, and the moderator is Alberto Cavallo from Italy. I will take care of the timing, so I will, but I think Alberto will also help me for that. I will run the timer, however, so everybody can see it in real time. Okay, Werner, the floor is yours.
Thank you very much for having me, and good afternoon to everyone. I think I will share my screen. Wait a minute. So we take the slideshow.
Yes, you could maybe try to go full screen.
Yes, but the slideshow doesn't happen. So that's the slideshow. Okay, today I'm speaking about technical and scientific engineering aspects of living in free space. With the next sheet. In space, there are a lot of engineering challenges which do not occur on Earth. For example, we need so-called artificial gravity or gravity simulation. We need some new construction technologies for rotating habitats. We need in situ resource utilization, or ISRU, of lunar and asteroid material. And then we have to have a look on the shape and of the geometry of rotating habitats in the future. Furthermore, it is important to look on the shielding against cosmic rays, solar flares, and meteorites. And last not least, we will have to create artificial biospheres in the future. Gravity simulations in rotating habitats. The simulation of gravity in rotating habitats is depending on the radius and on the rotation rate. Artificial gravity is in fact centripetal acceleration. For example, at the radius of about 40 meters and approximately 4 rounds per minute, we can simulate approximately 1 g artificial gravity. Next one. As an example, I want to show you an orbital station with a ring of rotating modules. The structure starts with 4 rotating living quarter modules. You can see it on the right side. And then step by step, it is enlarged with additional modules. On the left side, you can see the final stage of the station with a closed ring for about 180 persons of inhabitants. It is from the year 2017. Now there is, we can build modules either as inflatables or as rigid aluminum structures. Both methods have certain advantages. Inflatable structures in space need less payload capacity, but have to be filled with equipment after inflation. Heating and cooling of the outer skin is difficult. It seems to be difficult. On the other hand, rigid modules are equipped with the entire furniture and the wiring from the very beginning. The modules can be divided into separate rooms with rigid floors and walls, which you see on the right side below. There is a living and working area, and in the lower floor, there are private rooms with, of course, WC and so on. So if we have a look on the shape and on the geometry and on the methods of enlightening of different structures, the first one is a rotating ring or a torus. The material in this example from NASA, is coming from Earth, and the low gravity level is simulated. The second one in the middle is a sphere like the O'Neill's Island 1. It is a section of the Island 1 of Gerald O'Neill, but 1G artificial gravity can only be created on the equator, and for the enlightening, a complex mirror system is necessary. The third one on the right side is a cylindrical habitat. It has a maximum area of 1G simulated gravity, and in this example, the illumination is provided by central light distribution. This is a concept from the year 1993, where I was also a co-author. Next one. In situ resource utilization, or ISRU, and radiation shielding is very important. In the future, lunar and asteroid material will be important. Lunar regolith can be used as building and shielding material. So-called fused rock or lunarcrete would be made of regolith by a high-pressure melting and cooling process. Structures of lunarcrete bricks can carry high pressure loads, but are insufficient to tension forces. Tension loads can only be carried by steel or aluminum tubes or trusses, or by carbon fiber elements. These elements can also be produced in space factories in the future. Now, the last theme is how to create an artificial biosphere in space in a rotating colony. Huge cylindrical space habitats of some kilometers length need an artificial biosphere with a stable climate. A moderate climate, like in Sweden or Canada, needs at noon a solar radiation intensity of about 400 watt per square meter and hour. This is the minimum. The graph on the right side shows the daily curves of temperature and relative humidity. Land areas and lakes should be arranged symmetrically to balance the rotation of the habitat. You see it in the drawing on the right side below. Thank you for attention. This it was. Okay, I see I have just needed 8 minutes. If you have any questions, I can answer.
Yeah, if I may just ask a question. Do we really need 1G?
Yes, I think so, that in the future we will need 1G, maybe at the beginning for smaller stations, maybe we can make it with 80% or 90% of gravity. But I think in the long run, we will need 1G gravity because of the human health and of the human well-being in the future.
Thank you.
Another
Okay.
question. Hello, Alberto.
Hello. So thank you, Werner, for your presentation. If there are no more questions, oh, okay, I see one.
Yes,
Please, Aziz.
yes. With the gravity, is there like a lateral effect? Okay, since this is a centrifuge. Okay, is there like how is to deal with the effect if you walk on one side or the other side with the rotation?
Yes, there is the so-called Coriolis acceleration, but
Yes.
at large radius, at large radii, we can neglect this acceleration. When we have stations with small radius, we must be very careful about this Coriolis acceleration. So you are quite right with your critique.
Thank you.
Okay, other questions? If there are no more questions, we could switch to the next one that should be mine. So if I think we are exactly on time, so I would immediately start with my presentation. My name is Alberto Cavallo. I'm a member of the board of Space Renaissance and one of the founders. And I am happy that we have here three of the founders of the Space Renaissance, because we also have Patrick Collins today. So we have three of the five founders present today.
Yeah.
So anyway, my presentation, I'll share my screen in a few seconds. Okay. And then I'll move full screen. Okay. I hope you can see it.
Yes, perfect.
Yes.
Okay. So this is a presentation that I prepared some time ago, and I keep updating about the new era of the launchers, and it's concentrated on reusability. But mostly today I want to speak about a couple of things, not all the 60 slides, of course, we have no time for that. I immediately switch to the statistics of the last year, because for me it's very significant what happened, and it marks the fact that we are in the new era of space launch. Last year we had 217 launches from the United States. We had 94 launches from China. All the others are somehow residual. But it shows that the United States can count, of course, on reusable launchers, and we'll talk about that later. But also China is catching up, is almost just a slight below a half of the launches from the United States. All the others still rely on the old space way, and they are less numerous. Of course, 175 of the launches of last year are by SpaceX, of course. So it means that reusability have changed totally what is happening in space. But we had 69 launches by the national company of China. We had 23 launches by the Rocket Lab. I'll talk a little about that. And we also had 11 launches by Blue Origin. I think they have counted here also the suborbital launches, because they only had, I think, 2 launches last year of orbital launches by Blue Origin. It's essentially we are in the new era. We are in the era of usability. And now I will talk just very shortly about what is in service. That is Falcon 9 with a huge number of launches. Today I checked the numbers, so I updated to 657 completed missions. That is a number that is incredible if we refer to the past of space launches. And in 576 reflights. I won't go into details about the Falcon 9 because I think that everybody knows about the re-entry of the booster, the fact that essentially the rocket is 70% recoverable and so on. And we also have the Falcon Heavy that is essentially a larger version of Falcon 9 and with much less launches. And it, by the way, is a very powerful launcher with some limitations. A spectacular the fact that why is it not going on? Okay. That the re-entry of the side boosters happens, of course, at the same time. Now we have another competitor that is the New Glenn by Blue Origin, and it is essentially the level of reusability is the same of the Falcon 9, but it is much bigger. It's almost as big as in terms of the payload as the Falcon Heavy, but it has a larger fairing and a larger diameter of the rocket, so it can launch a larger volume of payload compared with the limitations of the Falcon Heavy. Unfortunately, well, New Glenn was successfully launched twice. In the second flight, it also carried the NASA's Escapade Mars mission that was launched first to a temporary orbit around the Earth and then moved on to Mars. Unfortunately, the third mission failed in terms of the fact that the second stage refused to relight. This is something that happens with new rockets. And then in May this year, they have this big explosion in Cape Canaveral. So unfortunately, like I said, New Glenn is in delay, and it will also affect the Artemis program, since the Blue Moon lander by Blue Origin is designed to be launched by the New Glenn. Anyway, we wish all the best to the people of Blue Origin to recover as soon as possible. I wanted to give a hint to Rocket Lab, because it is the second commercial launcher by number of flights, even if the Electron is not actually reused, even if it was designed to be reusable, but in fact they are not reusing much of it. But they had a large number of flights, commercial flights. They are extremely successful. They are the second launching company, with the exception of China. And then I skip the data because it's not. I immediately skip. This is what they try to recover it. Of course, we are all waiting for the Starship to start with the fully reusable biggest rocket ever made. After 12 test flights, they are not yet ready. And when they will, of course, it will be extremely important for us, because they promise to reduce the cost to orbit to a very low amount. And the numbers are extremely big. The total mass of 5,000 tons for the old version. This is referred to Block 2, but anyway, it's a payload to LEO is said to be from 100 to 150 tons. It's true that a lot of development is still needed. And we will see. Okay, I skip also the characteristics, only remind the spectacular way the first stage is recovered, because they don't want the further weight of the landing legs. I will want to skip to some new projects that are less known than the others I have talked about. But maybe they are known enough. But Rocket Lab is working at the neutron launcher. That is something that is in the class of the Falcon 9, but quite different from several points of view. It's very interesting because the first stage includes the fairing, because the second stage is located inside the fairing, and it will essentially perform like the Falcon 9, and with the performance that comparable. But the second stage is located inside the fairing, and it will not be reusable. But here we have something like a competitor of the Falcon 9 that could be operational, could start the test flights, maybe, hopefully, within this year. Another, I'll skip a little about the Relativity Space Terran. That is another competitor of the Falcon 9, but I would like to talk about a couple of other things because I find that the Stoke Space Nova is a very interesting project because it's designed to be fully reusable with a totally new concept. Because the first stage, of course, the concept is also the same. We are already accustomed to this kind of reusable first stages. But the second stage, by the way, the for performance is less than Falcon 9, but since it's fully reusable, of course the payload to orbit must be lower because the second stage is also recovered. The second stage is something extremely new because you can see that it is shaped like a capsule because it re-enters like a capsule and it uses the nozzle of the engine as a heat shield during re-entry. It's actively cooled, by the way.
Alberto, 1 minute.
Yes, yes. They have already tested the engine, and when they operated, it will be very interesting. And then we have the Chinese. I will immediately skip, since I have only 1 minute, to the test that the Chinese performed. Sorry, but it's a little slow in changing the slides. I will switch to this. This year, in March, there was a double test of the Chinese rocket to the moon because it is essentially a Long March 10 that will be used to launch the Chinese vehicles to the moon. It was the test included the first stage of the final rocket that is designed to be reusable, and it re-entered and splashed down in a controlled way on the sea, as you can see in the picture on the top right. And the capsule also recovered because it tested the rescue system. So they are already quite advanced in having a lunar reusable rocket, including the lunar capsule of China. And this is the latest news about about reusable rockets, and that it marks a great progress also from the Chinese side. That's all. Thank you. Okay. Stop sharing as soon as I can. Okay. Okay, so I think if you have questions, I think we have a little time.
Yeah, I think Jim Green.
Yes. Just curious about your thoughts on the Space Launch System, which is a working super heavy lift launch vehicle.
Yes, this presentation was concentrated on reusable launchers. So I just didn't talk about anything, didn't say anything about traditional expendable launchers. In my opinion, the reason is simple. I think that currently there is no future for expendable launchers, to be blunt. So I think that the SLS is extremely expensive, and it's not worthwhile to develop further this kind of rockets. And by the way, it was a regression because it uses components of the space shuttle that was reusable in a non-reusable way. I think that as soon as vehicles like the Starship are available, there is no reason to further develop rockets like the SLS. This is my opinion, of course. I take the responsibility.
I have a question. What development in Europe do you see for reusable rockets?
Yes, there are. I skipped that in the presentation because I had no time. But unfortunately, they are very slow because there is a test. There is a test item prepared by Ariane Group that is ready in Sweden, but it is. I could show it because I could switch to my. I have it on my presentation. if I can find it. Okay, I can share again the screen about this. Okay. Is this one. You can see that Ariane Themis project is for a test item that is comparable to the SpaceX Grasshopper, and they should be ready to test it this year. Unfortunately, they are just 14 years late compared with SpaceX, because this kind of tests were performed by SpaceX 14 years ago. Anyway, they are working at it. This is a real item ready to test.
Better late than never.
Yeah. Okay, so I think if there are no more questions, we could then move to the next presentation. Okay, so the next presentation is by Peter Swan. Peter, are you here?
Yes.
Yeah.
Yes.
Okay. We already had the presentation by Peter, and this one, of course, he's the soul of the space elevator. So he will talk to us about this very interesting topic. And I think one thing I spoke about reusable launchers, but a reusable launchers, you reuse the launcher, but the fuel, a space elevator doesn't need fuel. No. So Peter, the floor is yours.
Yes. I'll explain a little bit of that when I get there. It turns out that today we're going to look at the modern day space elevator, and we call it the modern day because we have the material for the tether. It's two-dimensional material. It was given a Nobel Prize about 15 years ago, and it's coming out of the library. So we're in pretty good shape with respect to the tether. This presentation is going to emphasize the sustainability side of developing space elevators inside a space economy. And so we're supporting, ISIC, our little organization, is supporting the SRI activities to have a UN number 18 added to its list of sustainability goals. One of the principal ways we do that is on the green road to space. And what I mean by that is we don't burn any fuel in the atmosphere, so we don't pollute the atmosphere, and we don't leave any debris along the way. So we really are supporting the concept of sustainable development in the Earth. And then we have such a major permanent infrastructure that will improve not only going to space, but also the support to the Earth, like space solar power and things like that. There are two or three major points I like to make in that we have an infrastructure. So we're making an infrastructure, and the curiosity that I keep seeing in my 56 years of working in the space arena, nobody asks what's the efficiency of a rocket, mainly because the rockets are the only way to get there. So we have to accept the fact that if we want to go to space beyond Earth, they only deliver less than 1% of the mass on the pad. Now, reusability is great and improves the cost effectiveness, the reliability, the speed of doing all kinds of stuff, but it still doesn't beat 1% of the mass delivered to the customer. So I keep asking in my small way when I go to presentations about what's the plans for logistic support. And so the way I want to approach it is space elevators will provide 70% of the pad on the mass on the pad to geosynchronous apex anchor, that's the other end of the tether, and into orbit around the moon and Mars because it doesn't consume any fuel along the way. 70%. In addition, we have a capability to, when we're fully operational, of delivering like 170,000 tons per year. Now, so far up to today, we've only put up 30,000 tons into orbit, plus or minus, but not that much. So we would have a huge increase in logistic support to the user out there beyond Earth. How does it work? Well, we've got 3 spaceports. We've got one on the surface, we've got one at geosynchronous and one at apex anchor. And what is a spaceport? It's a truck stop. You accept satellites coming in, you release satellites going out, you repair satellites, you refuel satellites, store, and then assemble a larger spacecraft. I worked at JPL for a while, and I was always curious about how come the satellites are so small. And then when you start getting into it, you find out that the payloads have to share battery time and storage of information time and comm times because they don't have enough. Well, we can assemble something at the apex anchor. Let's say we assemble 10 payloads of 10 tethered climbers. That'd be 140 tons that we could have in a science spacecraft. And you can have all kinds of missions with that. And then you release it, it goes any place in the solar system. It's pretty straightforward. Okay, so we have galactic harbors as the concept, which would be 2 tethers in one spaceport on the ground. That way you have up and down, or you could do both up, depending on how you want. But we can move massive, massive tonnage. It looks like this on the deployment of the system. So we get up to 170,000 tons per year. It's a green road to space with massive tonnage. So we call it the logistics giant of the future. We can supply the parts that you need out to build rotating settlements and stuff like that. What are the strengths? Well, we've got an unmatched delivery efficiency, 70%. Rockets, aren't even measurable there. Green road to space. We have unmatched velocities. We release from the apex anchor. Arizona State University students actually did the calculations on this in their orbits class. We can release from the apex anchor at 100,000 kilometers and go to Mars with no energy. Now, of course, we got to change the plane a little bit. So we got to have rockets. We got to slow down when we get there. We got to land. So we need rockets. I love rockets. But if you get off the Earth with a space elevator, you have so many advantages. So we have unmatched delivery, and we've got green road daily to Mars. Oh, by the way, we can get there in 61 days. No 26-month delay for the alignment of the planets because we go so fast. And we've got the assembly at the apex anchor that people don't really think about. They think if you launch it, it's gone. No, we can lift off and assemble. Okay, getting back to the unmatched efficiencies, rockets are draconian. I love rockets. I was in an Apollo launch. I supported launches all the time in my whole career. I love rockets, but you've got to realize they don't deliver diddly squat. They have a horrible record, and you're not going to improve it just because you do reusability. Makes it less expensive and all that. So let's look at what we can provide with this permanent infrastructure with massive delivery. We can help space solar power. We can put those, the minimum size for space solar power satellite is 2,000 tons. I don't know if you guys follow John Mankins and his activities. The normal size is about 4,000 tons for one satellite for space solar power. We need space solar power. I'm a big supporter of it. But trying to do rockets up there is a little bit tough. As with the green road to space, we're going to really take care of our environment. We're going to support the ideas that our environment is very important and the health of the Earth is key. So part of the UN sustainability goals is, pollution control. So we believe we can do that. We can help the sustainability on Earth through space by completing the missions in space, planetary defense, space solar power, disaster communications, all that. We can provide capability to go to GEO very simply, and they can have huge spacecraft up there. You can assemble up to 4,000 tons easy at the geosynchronous spaceport. So we can help the community in their mission, individual missions as they go along. We provide the capability to get there. We call it logistics. It's kind of an important term that people don't talk about very much. And in orbit growth, you know, we bring up that much mass, we can really, really help. And we're 24/7, 365. In our architecture, we look at is 6 space elevators or 3 galactic harbors. So we really want to enhance. And by the way, we're a partner of SRI. Thank you for the partnership. We just signed that at the NSS, National Space Society meeting last month. So we're a partner, and we did sign the motion to go forward with number 18. So we support those ideas big time. And if you go to the individual aspect of those different global goals, if you have the capability to move massive stuff to GEO, then you really can support these missions very nicely. Climate.
1 minute, Peter, 1 minute.
Okay. So the value propositions is we're a logistics giant, and we can do all kinds of massive movement to different places. This is just one example of putting the data centers up in space. We can assemble them at geosynchronous or apex anchor. The students at ASU came up with their study, and they came up with 3 or 4 things that are really neat. Now, these students did the study and came up with these numbers. But in addition, they came up with a bus schedule. Can you imagine a bus schedule going to Mars? On Tuesday, you leave from the Indian space elevator. On Wednesday, you leave from the Pacific. All that kind of stuff. We do have our material. You can do a lot of research on our website for that. And we've got 16 2-year studies. I'm a member of the Academy, International Academy of Astronautics. So we paralleled that and did studies. So go to our website and do that. And here's 2 magazines. BIS supported us greatly there. So basically, I'm done. Any questions?
Yes, Walter Hammond, I've got a question. What about cutting these space elevators? In other words, you could have an aircraft or any kind of object flying into the space elevator at such a big distance. If you have multiple space elevators, makes the problem worse. Could you address that problem?
It's a probability thing. We've done 2 studies, 2-year-long studies. I actually tracked satellites for a year, and I actually calculated conjunctions in space. So I know the numbers. They're calculated, and they show the time. We must move the space elevator out of the way of big things like space stations. And we can do that by moving the bottom earth port, or we can move the tether climber along the way, and that disturbs the motion of the tether. We can move the tether out of the way of the big stuff, and the small stuff's not going to hurt. This material is infinitely strong. You wouldn't believe the strength of this material. That's part of the criteria for picking the graphene superlaminate, in that they're so hard. But you can go to our study and look at the space debris. Another aspect of space debris is one of the options we're planning. We don't have our final architecture yet on the design of this. I've proposed that we have 6 legs coming down from 2,000 kilometers. What we do is we have light legs that would back up if the principal one were cut, but we also put science experiments on those legs. We also put a commercial hotel at 400 kilometers up. The legs have missions by themselves, but the principal one would be to back up in case there's a LEO conjunction. We believe we can operate safely inside there, and the numbers, it's the same as if you launch 2 or 3 rockets. It's the same numbers each time. You know, that statistical issue is a little false. You've got the individual events that are occurring.
I think we have another question by Mike Helton.
Yes, I think this elevator process would be considered a lot more serious if you could make a very small demonstration of it, say in very low Earth orbit, that would require not so much graphene to make a cable. So is it possible to make a very small demonstration model?
We've had 14 tethered satellites in orbit by students and experiments. So we've done much of what you're talking about. Yes, we are going to do an experimental space elevator in low Earth orbit with all probability. We don't have our development plan finalized, but we've got to test it. My current idea is we drop we drop 1 mile cable from a bridge in New Mexico that's over the Rio Grande, and it's a mile long, and then you could do testing on that. And it would have to be the material that we want to use and all that kind of stuff. But yeah, we would do the testing of the material. So there's no doubt about it. We'd have tests, just like you do any testing like rockets. We'd have potential tests along the way, this long, this big, tether climber 1/3 size, tether climber full size. We've got all those plans in our minds laid out in our architectural approach and all that. Yes, we have to do a lot of testing to go forward.
Thank you.
Okay. Thank you, Peter, for this wonderful presentation. I think we can move to the next one. And the next one is about space elevators, because we have Dennis Wright. Dennis, are you here?
Alberto, sorry, I put it in the chat. I thought you had seen it. I propose to let Patrick to talk next, because he's maybe 11 in the night at his, so he will not remain too long awake. What do you think? Can we do it?
Of course.
It's okay with me.
So Patrick, if you are ready, we can shift your presentation here, and then we can take back the normal sequence.
Okay, sure. Adriano, can you do my slides, please?
I hope so.
I sent you the PDF.
Sorry, because I was not ready to do that, but if I have your slide, for sure I can show it. Papers. Collins, yes.
So in the meanwhile, I remember that Patrick Collins is one of the founders of Space Renaissance, and he's a long-time friend for all of us, and he in his extremely long career, he talked from space topics, but also economics in Japan, and he is very much active in about space tourism and other things he will talk to us about.
Yeah, thanks very much. It's a very nice memory of the early days. But it's tremendous growth since then, thanks to all your huge efforts. So I'd really first say thank you to Adriana and Alberto and the team, and congratulations. It's really terrific where we've reached now. As you say, I'm retired, but I work with the SSTJ, Society for Space Tourism of Japan, and there we our view is simply that traveling to space should be like traveling in air travel. You should be able to buy a ticket and go to space. So next slide, please. It isn't the space age. A lot of people talk about how space is, the space industry is growing and growing, and it is, and it's great. But it's not the space age. The space age is when we can get to space, just as an ordinary part of daily life. And so next slide, please. So just 3 points about space tourism. First of all, space tourism is very different from the space industry as it is today, which is very largely, as I just noted there, data services, and that's fine. Space technology has made terrific progress in all sorts of different ways. But as it says here, carrying passengers like airlines is just completely different from the work of space agencies. And indeed, as you probably know, the US government already 20 years ago made the FAA formally responsible for regulating space travel, because it's precisely the same business model as air travel. So next slide, please. Another thing to remember, I'm sorry, but we can't see the bottom of the picture here, but a suborbital spaceflight happened in 1942, okay? And then they also put wings on the prototype rocket and flew it. And they designed, as you can see here, a fully reusable piloted version, but they weren't able to fly that towards the end of the war. And after the war, the engineers were all forced to build ICBMs. But they could have flown fully reusable piloted suborbital space plane by 1950. What happened was, of course, the X-15, the American X-15, very famously flew repeatedly on suborbital flights up to space and back through the 60s, and was then cancelled in 68. And no more space planes were built for 36 years until Spaceship One in 2004. And we've had another 22 years since then, and we still don't have even a proper suborbital passenger space flight service yet. So next slide, please. And another point about space tourism is, all businesses grow and grow, and space tourism has terrific space to grow, starting with suborbital. And on the bottom left here, these are a couple of Japanese projects, which, they're not properly funded yet, but they're both, moving forward pretty well. So even in Japan, I think we'll have suborbital space travel within a few years, beginning, and it should by then be, starting to boom in America, I would guess, and also Russia and China both working on it. So in the middle here, we have something like what might be a two-stage orbital space plane, big booster vehicle with a orbiter on top. And of course, space hotels several companies have already put their hats in the ring and want to build space hotels, but they have to wait until somebody has a serious plan for a passenger service to orbit. And then on the far right is a picture from 1987 by Obayashi, big Japanese construction company, of a resort on the moon. And this is before the internet, and the building is designed so that you can see it. Couldn't be on Earth. You couldn't build that on Earth, but you can in the 1/6 gravity of the moon. Obayashi works considerably on space elevators as well. So next slide, please. It's kind of big economic issue we have to face, though, about why has the space industry not developed space tourism? It seems it's kind of the obvious thing to do in democratic capitalistic countries. And this is to do with the way, government budgets have got terribly distorted by huge vested interests. And the biggest vested interest is the military. And as you know, in America now, it's reached up to it's growing to over $1 trillion a year. And the next slide, please. This is already 10 years ago, but this is the United States military budget compared to the rest of the world. And you can see it's not a defense budget. And indeed, just recently, as you probably know, the name was changed. It's now the war budget. It's the Department of War. And this is just a huge distortion of government spending. And a lot of aerospace, of course, is related to this. And the next slide, please. This did you notice this? This was very interesting. President Trump went to visit President Xi in Beijing, and at one of the public speeches, President Xi even mentioned Thucydides' trap, which is his famous observation by an ancient Greek historian who noted that a lot of empires, once they're beginning to decline, they often kind of commit suicide by having a final huge war to try to crush down the competitors, which they're losing relative position towards. And so, this is we're in a very dangerous moment in history. So but there's an economic issue here. So next slide, please. Oh, no, this is just part of this process, this Thucydides traps, the bricks growing and growing because of America's attempts to prevent competition, and so it's a vicious circle. I mean, it's a very interesting problem for a superpower. So next slide, please. It's much more cost effective to have arms control treaties. But then again, of course, the USA recently has ended all the arms control treaties. So, but the next issue is the key one. With such a gigantic budget, let's say the US war budget was cut by even a third. It's up to 1.5 trillion now, I think. This would cause a recession. If you cut 500 billion per year of aerospace industry work, it's mostly aerospace related. This is a very serious problem, and they won't do it unless there's at least some substitute available. So next slide, please. Space tourism has a unique potential, as it says, to wean aerospace companies off military funding. They're aerospace, and because they're passenger transportation, have huge potential growth. What I call the big six passenger transportation industries of history, each spread worldwide. So if the next slide, please, the picture. Just shows it. Horse carriages, sailing ships, trains, steam propeller-driven ships, cars, and airplanes. Each of these inventions transformed the world. These technologies spread around the entire world and created literally hundreds of millions of jobs, directly and indirectly, in the industries they enabled. So next slide, please. Rocket propulsion is the seventh potentially big space transportation industry, but it hasn't, as it says, it's barely started to be used yet for passenger travel, which is the big use of these other transportation industries. This is a picture I produced about 20 years ago now, but don't have time to mention it in great detail. But employment we're getting new employment from new industries all the time and losing it through competition, productivity growth, and so on. But we've got this $1 trillion investment. Well, it's probably about $2 trillion have been spent around the world on space development, but still there's no $1 trillion space industry. There should be by now, but that's, in my opinion, because they haven't developed space passenger space travel. So next slide, please. This is the left-hand side is the graph of basically the growth of passenger air travel. We're up to 4 billion people a year. That's 10 million a day. It's still growing, doubling every 10 years. So it'll soon be 8 billion and then 16 billion. This gigantic, popular business, travel. And so the right-hand side is the 21st century, how space travel could grow. And I've still, in 40 years of working on this, I've never come across any reason to doubt that this is possible. It's just that space agencies don't do it. And the commercial space industry still hasn't really got its teeth into it, but I'm hoping it will quite soon. So next slide, please. This is, the AI story that it's threatening to eliminate hundreds of millions of jobs. If that happens, if we're to keep society anything like we have, where, people work for their livings, we need huge new demand. And so as an example of what could happen, we could say children need to have space travel experience in as part of their education. All children, the current one would be suborbital, but in a decade or two, they would all take an orbital trip, and then later on.
1 minute, Patrick.
Thanks very much.
Okay.
That's great. My next slide is the last one. So next slide, please.
Okay.
This will be extremely educational. I've been, working on and off on a space travel curriculum, which is a way of basically including almost all topics within the topic of we're going to travel to space. As it says here, will infuse generations with a vision of a bright future, instead of the dystopian future vision of resource wars, which they're bombarded with. Depression and self-harm and stuff at record levels all around the rich countries, because children are given such a gloomy vision of the future. And this would be one way, I think, of helping to counteract that. It just needs more, I think, recognition that this is a possible future. So I'll leave it there. Thanks very much.
Thank you, Patrick, for this fantastic presentation. We discussed these topics long ago.
long ago.
And you are right. This dream that so many children can see the Earth from outside, this is the best possible implementation of the overview effect.
That's right. That's right. Education. As part of the education of what it is to be a human in the 21st century. Yeah.
Thank you. If there are no questions, then we can move to the next.
I just have a small comment, Alberto. I think, Patrick, your note about the 8 trillion deficit USA. I don't know if the figure is correct. That I don't remember.
40 trillion debt. Yeah.
Yeah, is the sum of the military expenses of the last good number of years, correct?
More or less, yeah.
I think this is an important concept because we are thinking it's raised in this Congress, and we are thinking to run a campaign for the conversion of the military industry to civilian space industry. That will save the jobs, and will save civilization.
Save civilization, yeah.
So thank you very much for this data. I think we can take it from your paper and insert it in our campaign tools, let me say. Oh, okay.
Right. You should be aware it's a round figure.
Thank you very much.
It's not precisely calculated, no, but $500 billion a year for, what, 80 years? It comes to 40 trillion.
In a rough way, it corresponds to the reality, because this,
that's right.
Yeah, this 3 trillion per year of military expenditure, global, it's crazy. It's crazy.
Yeah.
And
it
the
is drones. The
drone
industry is driving people crazy. We're going to make 1 million drones a month, in factories.
Exactly. Okay.
Yeah.
Thank you so much.
Thank you.
Okay, so I think we can go back to the order of the presentations. So the next one is by Dennis Wright, president of the International Space Elevator Consortium. So we are back to space elevators. So Dennis, the floor is yours.
Thank you. I would like to introduce you to the International Space Elevator Consortium. It's an organization that's been around for more than 20 years now. And I'd like to talk a little bit about space elevators, what they are, and how the development is going, and then talk about our main functions in the organization. So we have 4 missions. First is to promote the space elevator development. We support and engage research into space elevators and related topics. The knowledge base for space elevators has been growing, so it's one of our jobs to curate and expand the knowledge base. And of course, we want to spread the word. We want to educate people about the space elevator and its advantages. So what is space elevator? Many variations. Could be skyhooks, could be launch loops, things like that. But I think the simplest design, and one which we concentrate on, is a single tether from the Earth to about 100,000 kilometers. There is an apex anchor at that altitude. The climber ascends the tether, and the tether then transmits Earth's rotational energy to the climber. So the whole system is gravitationally stable, and we prefer to base it at the equator to take advantage of the maximum rotational velocity. It doesn't have to be on the equator, but that's the best place. So space elevators are the best way to get out of the Earth's gravity well. Much less costly, more efficient, cleaner, safer than rockets, and it can do things that rockets just can't do. So I think the most important thing is that it potentially has a much higher mass throughput than rockets. So this is the only alternative, I would say, that really can enable large-scale space settlement. And it can become the basis of an interplanetary transportation infrastructure. So space elevators are a lot closer than a lot of people think. The materials exist in the lab and have for some time. Climbers, a recent study we did showed that you could actually build one today with today's technology. Many architectures for the space elevator exist, and the current one has matured over several years, so there will certainly be changes as developments go along. Most importantly, I think we have the materials, but now we need to look at large-scale manufacturing. So getting them out of the laboratory and into the factory is the next big step. The electric motors that drive the climber are crucial. So Pete likes to say that he would like a 70% payload on the climber. So far, we've demonstrated we could do 50. So the motors need to improve, and I think that's possible. So we could get to 70%. As the designs and technologies advance, the architectures will change, and ISEC is involved in all of these areas. So let me talk about two of them. One is the material, which you've heard about already, but two of them are allotropes of carbon. First one discovered was carbon nanotubes. And the second, and the one that we like the best, is single crystal graphene, which would be layered up in thousands of layers to make a tether. And then the third possibility is hexagonal boron nitride. So all of these are strong enough to be the tether material. The climber, we did a study 2023, and then more recently want to consider powering the climber. And this is a design for a 20-ton climber with a 10-ton payload. And it's based on a friction grip. So counter-rotating wheels pinch the tether and pull up the climber that way. So we're using electric motors, and the electric motors used so far, we're thinking beamed power is the best way to do it. We have an extensive research function. We do studies, at least one in-depth study each year. We pick a topic that we think is important to the space elevator and go as far into it as we can. Publish the results either in academic journals or in the ISEC webpage. So if you want to see any of these studies, go to isec.org, and you can get them all for free if you'd like to dive into any one particular area. We support all the participation in engineering and lab work. So ISEC members are parts of groups that develop materials and engineer the climbers. And we're also encouraging universities to get involved, and more importantly, perhaps industries to invest in the early stages of the both the material development and the climber development. So 1991 was the advent of carbon nanotubes, and then graphene came along in 2004. And since then, space elevator research and knowledge has really increased. And so we figured it was our duty to keep track of all of this and collect it all into one place, or at least everything that we could find. And so we have papers and studies, and we build and continue to add to the database with study reports and a bibliography, reference library, and architecture notes, and videos, and space elevator history. So all of that's available at our website. We have published in several journals, Acta Astronautica, Journal of the British Interplanetary Society, National Space Society, Ad Astra, and Spaceflight Magazine. A big job we have is spreading the word. So we do this in several ways. We have interns. These are both summer students who are either upper university or upper high school or university students, and technical interns. So occasionally we'll have a project that we're working on, and we will put out an advertisement for somebody who can provide some technical assistance, a little bit more in depth than what the summer students can provide. We are partners with many organizations, most recently Space Renaissance. We signed partnership agreement at ISDC this year, but we're also partners with National Space Society, British Interplanetary Society, Japan Space Elevator Association, and the World Space Elevator Competitions. And I'll say a little bit more about that because that's a new area that we're getting into. So competitions have been going on for some time. I think the first one was the NASA prizes for space elevator competitions, in which they offered prizes for power, beaming, materials, and climber design. And those have now been continued, probably more in depth than anywhere else in Japan, through the Japan Space Elevator Association, where they have climber competitions more or less regularly. And the World Space Elevator Competitions wants to broaden that. So they are now planning a workshop climber competition in Kazakhstan in October, I believe. So there's going to be a competition there. And we want to also bring the climber elevator concept to middle and high school universities. And so at ISDC, we had 2 workshops in which people would be given a kit to basically develop a little Lego style climber. And they would build them and then put them on our demonstration kit and try to see if they could reach the ceiling. So we do that. The photo to the right there is a Japanese team.
Dennis, 1 minute.
Thank you. Japanese team examining their climber before it goes up the tether, which you can see stretching off into the distance. So we believe that space elevators are going to be an essential component for moving humanity off planet. They're a lot closer than most people think. Components of it can be built today. We promote the development through technical studies and encouragement of investors and education. And of course, as always, we are a volunteer organization. We exist solely on donations and membership dues. And so we depend on volunteers to get us going and keep us going. And if you are interested, please visit www.isec.org. Thank you.
Thank you, Dennis, for this extremely important presentation about what is going on for concretely about space elevators. They are not just a concept, it's something that is happening. If there are any questions, then
I have one question. I have one question. Do you have a photograph of a graphene cable that's 10 feet long or longer? I'd like to see a photograph.
10 feet? No. The only existing piece made of single crystal graphene is about 1 meter long.
1 meter?
1 meter. And there are pieces of polycrystalline graphene as long as 1 kilometer, but I don't have a picture of that.
Okay. I think that would be good for your presentation, is to have some photographs of real material and not fictitious diagrams that look like they would be the case. But you know, if rockets did not exist, and I came to you and I said, let's build a Saturn V rocket, what wonderful things we can do, and I wrote a book about it, you wouldn't believe me. You would say, well, how does a rocket work? And I could go in my garage and make a small rocket and go up to 10 feet. And then you could say, oh my gosh, we could do that. So I'd like to see a small version that really works. Then we can talk about a big version.
Yes, I certainly agree. We are trying to convince companies to produce bigger pieces. And certainly the polycrystalline could be used right now for just such a purpose. So we just have to get a chunk of it.
Okay, thank you.
okay.
Could I ask just a quick question?
Please.
Satellites. With people talking about putting 40,000 satellites and 100,000 satellites into orbit, surely these are gonna be a problem, aren't they?
As long as we know the orbit, there's something we can do about it. So the tether itself is going to be a stretched string vibrating, and the period of vibration can be changed. So we think we can use that to do avoidance, and the probability of collision is pretty low. So yes, it is complicating the matter for sure, but I think it's still a manageable problem.
Thanks. Yeah, I want space hotels, so I don't like 40,000 satellites either. Maybe we can have an anti-satellite consortium.
Yeah.
Okay. So I think we can move to the next presentation now. The next one is by Ghanim Alotaibi, our member, SRI member, and also responsible for the young generations and other things. But today he will talk about solar power. That is one of the important topics that we are covering. So Ghanim, if you are ready.
Yes, I am ready.
Yes.
Now I am sharing my screen.
Okay. The floor is yours.
Thank you. Do you see my full screen now?
Yes.
Yes.
All right. So thank you very much for this opportunity. Of course, I was honored to be part of SRI community since 2022. And I am currently doing my PhD in space-based solar power. I am more into the technical part. I am doing thermal management, designing radiators. But today's presentation is more about trying to convince policymakers. So this is my outline. The core of this presentation is to show that there are fundamental differences between the current solar power satellite companies that are being working today, the today's trend, and Gerard O'Neill's vision. Today's companies are actually their main objective is to produce power energy, to utilities in Earth. But Gerard O'Neill actually had solar power satellite as a product for a huge settlement in space, in Lagrange 5 points. So in the end of the presentation, I will try to communicate the idea of how the current trend can be important for future large-scale structure and large-scale habitats in space. So very quickly, of course, we have space-based solar power. What you are seeing here is the SPS Alpha. Actually, this is the older version by John Mankins. There are hundreds of different concepts. This is one of them. This is hypermodular concept. In the top here, you see reflecting mirrors. Any direction from the solar irradiance can be reflected and concentrated into the solar photovoltaics down here. And then the solar photovoltaics will convert the solar irradiance into DC currents. In the bottom, which is not shown in the picture, we have wireless power transmitter. It will take the DC current and then convert it to microwave. There are other concepts that uses laser, but in this one, it's microwave. And then beams it down to Earth, where you will have a rectangle in the ground, and then it will send it to wherever it needs in the network. It is surprising to say that, it might be surprising to say that the end-to-end efficiency is similar to terrestrial silicon-based photovoltaics. So we are talking about 18%, 20% efficiency. But the advantage of this, of course, you have 24/7 power. So you have base load power can be delivered by this system. Quick history. So as similar to many other innovations, it started by a novel by Isaac Asimov. And then in 1968, Peter Glaser patented the idea. As you can see here to the lower right, this is a monolithic concept, a huge system, very huge system. You have the wireless power transmitter like a dish. So yeah, it is completely different than this concept where it's hyper modular. While this concept is monolithic. In 76, O'Neill published the High Frontier book, and he proposed solar power satellite to be as an industrial product from large habitats. We will be talking about this. In the 70s, there was a serious study by NASA and the Department of Energy. They concluded that although it might be technically possible, the commercial viability is still not possible at that time, and they recommended to have another study afterward, after 10 years, after a decade from that. However, recently, in the last few years, we started to see a revival in solar power satellite, and new companies actually was established. Why we are seeing this, as has been repeatedly mentioned in this conference, we have lower launch costs, we have growing energy demand, and important idea here is the energy independence. Countries, especially in Europe and Japan, they need independence given what's going on in the Ukrainian war and also what's going on in Hormuz Strait. So solar power satellite is coming back. The maturity of technology make it more promising. Some studies has been published showing that there might be some niche market that makes solar power satellite not only technically feasible, but also with potential for commercialization. So today we have this model, solar power satellite to be manufactured in Earth using Earth resources, to be launched mostly to GEO. Those are most concepts. There are other concepts not in GEO. Beam power down to Earth and then sell electricity. And of course, there are companies, TerraSpark and Solar Power Satellite. Those companies actually in Europe, and they raised some funds. They are planning for demonstrators by the end of 2028, 2029, and a full scale, a gigawatt scale by 3035. So this is what's going on right now. Gerard O'Neill had a different perspective, of course. So I'm not going to repeat this slide again. He proposed a rotating habitat. There are advantages for this. You have 24/7. The rotating habitat in Lagrangian point has access to power 24/7. He proposed one of his islands, one of his cylinders, to have 3 villages. Each village will be working different shifts so that the entire habitat will have 24/7 labor work. Of course, you can control the climate and so on. The most interesting part here is the industrial facility. Within, of course, there is a different cylinder. The industrial facility will produce goods, and the first important product was proposed to be solar power satellite. So this is a different approach, different perspective. We will be launching lunar resources using mass drivers for the orbital manufacturing process in L5 or the O'Neill cylinder. Then we will have laborers working to produce solar power satellite and then sell electricity to the ground. This is fundamentally different from what's going on right now, because here, solar power satellite is a product and it's an essential part for an entire ecosystem. Unlike the current situation where solar power satellite companies are utility or electricity providers, if you like. You can see here the differences. I have summarized the differences in this table. So from Earth resources, of course, here, and O'Neill's paradigm is from moon and asteroids resources. The real remedy here is the launch dependency and scalability, because of course, if you want to launch more satellites, although the launch cost is getting reduced dramatically, we are still limited with the launch vehicle. And this is also putting a lot of stress on Earth. Unlike creating an entire ecosystem by building satellites from lunar resources. I'm afraid the time is really fast. So basically, O'Neill's paradigm is a revolution where we have a new economy created, while today's commercial paradigm is an evolution. There is, of course, a save in carbon.
Ghanim, your time is over. I'm sorry that I gave you the warning at 1 minute. I'm sorry, because I was
so yeah, sure, but I have only my last slide. So I'm gonna conclude here. So what's going on right now? We have current companies are doing phase 1 and phase 2. This will be extremely important. However, decision makers and also the startups should be aware that this is limited. Scalability is limited, and we need to think about utilizing lunar resources and the knowledge gained from phase 1 and phase 2 to start manufacturing in space and create an entire ecosystem that is not limited by scalability. Thank you very much.
Thank you, Ghanim. Yes, very good presentation and very good the concept of putting O'Neill's ideas on the space-based solar power. And we discussed about this and we agree. And if there are any questions, otherwise we will go to the next presentation.
If no one else, I would
go quickly because we don't have so much time.
I think the O'Neill perspective is very good, inserted in your picture, in your perspective, Ghanim. And I believe that maybe we should discuss about the last tendencies that are rising up. That is, instead of bringing more energy on Earth, to move the users outside. This tendency is becoming evident with the data centers, because now that the main dealers are thinking to move the big data centers in orbit, because they will be directly fed by the sun 24/24, and they will not have the big problem of cooling that they have on Earth, where that they need a lot of fresh water to cool these big servers, big supercomputers. So therefore, I also think that in the Jeff Bezos plan to progressively move the industrial development in orbit in the Lagrangian points and the civilunar space is on the same road to move the big users, big energy users outside. And I also think that in the roadmap that in the O'Neill roadmap that you show, the last stage is to sell energy to Earth, but at that point, when the O'Neill communities will be well rooted in space and the expansion will be on its road, maybe Earth will not need any more energy from space, because the most of industrial activity will be outside, and on Earth we will have, let me say, stewardship activities and so on. I mean, tourists and other things, of course, commercial and so on. But that big need for energy will be moved outside, and so this is, I think, it's the perspective that we can. The best perspective that we can see, because of course, if the wars continue and the civilization will implode, nothing makes sense anymore. I'm sorry for my long comment, Ghanim, but I think it's very important in our Congress to have a clear perspective of of the civilian space development.
Okay.
I agree with you, of course. The more demand, the more labor work will be created by a settlement, on your settlement, more migration, and less demand, electrical demand in the ground, in Earth.
Okay, good. So now we can move to the next presentation. We have again Werner, who is also the chair of this this session, who will present space-to-space transport systems with the contribution also of Walter Hammond, who designed the propulsion part. So I leave the floor to them. Please, Werner, and then Walter, organize your presentation.
Thank you very much, Alberto. So I try to share my screen. What's the other one? Wait a minute. That's exactly what. I hope you can see my.
Not yet.
No?
Not yet.
No.
Not yet. Not yet. Okay. Wait a minute. Why does this not happen? Now it should function.
It's arriving.
Yes, yes.
Yes, okay. I try to click the slideshow. So, okay, I am speaking with together with Walter Hammond about the space-to-space transport system. Now, when civilization is expanding into space, we will need vehicles which provide comfort for civilians and protect the health of passengers by simulated gravity, especially for travel between Earth orbit, lunar orbit, and the Lagrange points L4 and L5. The goal is to design some kind of space cruiser as a flying hotel in space. So our first design approach was to create a space-to-space vehicle for cislunar space. This vehicle is designed as a modular construction. The modules are assembled in low Earth orbit. The length is about 100 meters. The diameter is about 67 meters. The dry mass of the vehicle is approximately 340 tons. It has 3 rotating passenger modules for 18 passengers and 6 crew members, which is about 24 humans. Now, I have calculated a round trip from low Earth orbit to low lunar orbit and return to low Earth orbit. We have decided to use nuclear thermal propulsion, 6 nuclear thermal propulsion engines, each one about 178.4 kilonewton, which will give a total thrust about 1.07 meganewton. The reactor thermal power at the peak is about 6 gigawatt thermal. Now the liquid hydrogen tanks are approximately 700 tons, which is about 9,819 cubic meters. You see on the left side, you see a sketch. This is a side view where you can see all the. Okay. Now, nuclear thermal propulsion. It is based upon a reactor which high assay, low enriched uranium plus 19.75% of the isotope U-235, and this is generating heat. Liquid hydrogen is pumped through the reactor core and generates thrust. So the fuel is liquid hydrogen. Now let's have a look at a living quarter module for 8 persons. By changing the rotation rate, gravity simulation between 0.4 and 0.8 G can be created. The effects of different G levels on the human body can be studied. If you look at the section on the left side, you can see there are 2 floors, and on the right side you see the upper floor, which is the living and working area, and the lower floor is the dormitory with 6 rooms, including shower cubicles and toilets. So the next step would be an advanced multi-purpose space cruiser to Moon and Mars. It is not just a vehicle for transport, but also a rotating space station for lunar orbit and in Mars orbit. The length is about 125 meters. The diameter is about 80 meters. There are 6 passenger modules for 36 passengers and 12 crew members. The dry mass is about 698 tons. In the journey to Mars, which will last about 260 days, it is necessary to refill the fuel tanks by liquid hydrogen, by ISRU, by in situ resource utilization. The cruiser has to stay approximately 500 days in Mars orbit and then return to low Earth orbit in exactly 260 days. Now we need 16 nuclear thermal propulsion engines with a thrust of 1.78 meganewton. The reactor thermal power is about 9 to 10 gigawatts. And the liquid hydrogen tanks are about 835 tons, which is about 12,400 cubic meters for one-way travel. And they have to be refilled in Martian orbit. During the 500 days in Mars orbit, the tanks are filled with liquid hydrogen, which is produced on the Martian surface. Clearly, a Martian outpost has to be established some years before the first MPSC can travel with civilians to Mars. What is important is that each maneuver requires specific liquid hydrogen tanks. When it's about 4 tanks for the transfer to Mars. For Mars orbit arrival, we need about 2 small tanks. For the transfer to Earth back, we need also 2 tanks. And for Earth orbit arrival, we need also 2 special tanks. We have
1 minute.
We have designed, yes, we have designed 2 engine modules. If there is each one with 8 nuclear power and nuclear power thermal engine. Now, I would like that our co-author, Mr. Hammond, may have some sentences which he can add to my
yes, I have some questions or a comment real quick. The nuclear thermal propulsion won out over chemical rocket by a large margin because the specific impulse is so much higher with the nuclear reactor than conventional chemical propulsion. And the tankage, we still assembling this large structure in orbit is going to take some amount of launches, probably using the big SpaceX or its successor. And assembling the tanks in orbit is one issue I haven't really addressed very well because these are large tanks. They could either be assembled in orbit. If you have to launch them from the Earth already assembled, they're going to be thinner than what is shown here, I think, because they're too wide, right?
They could be expandable, of course.
Yes, right.
Could be expandable.
Okay, so the details are in our paper. You can look at the paper and it has links to how I did the propulsion analysis.
Yes. Okay, thank you, Walter, for your comments.
Thank you very much, Werner and Walter. I have a question that is, have you thought about the problem of boiling off of the hydrogen during this long travel?
Yes, excellent question. One thing that I might, the use of graphene, in other words, hydrogen leakage is a big concern for long-term hydrogen storage on the way to Mars and on orbit in Mars. And this is a problem. One thing that I was thinking about is graphene, some kind of coating. Graphene is almost impermeable because the spacing in the atoms is very, very close, but I don't know, that needs to be studied. There could be other measures taken. This is something that requires future analysis and effort.
Thank you.
May I suggest, Walter, that the graphene wouldn't be applied like that. It would be graphene sheets. And that's what we are talking about, the 2-dimensional sheets. You can wrap that around and that would provide what you're looking for, atom to atom material that would not allow hydrogen to escape. So yeah, the new material, the 2-dimensional material, would be perfect for that. It turns out much of that's being done at the University of Manchester. And I kind of talked to them a little bit a while back about the space usage. And one of the things I suggested was rocket fuel tanks would be an excellent use of the 2-dimensional sheets. If you want to check on that, University of Manchester has a lot of that.
Okay, thank you, Peter.
Okay, thank you all. I think now we can move to the next presentation. The next one is by Giancarlo Genta.
Yes.
Yeah. Okay, Giancarlo Genta is a professor emeritus of Politecnico di Torino, and also he was also head of the Department of Mechanics and then head of the course, coordinated the PhD course on mechatronics. But now he will talk to us about interstellar colonization.
Okay, so let me open. Is connected?
Yes, it is.
Okay, it is all right now. It should be full screen.
Yes, it is.
Okay. So the title is Interstellar Colonization, Will It Be Possible and When? Because the distances in interstellar space are so large that many think that it is impossible to get away from the solar system. But if we want to become a truly spacefaring civilization, we should try at least to get out. Nuclear thrusters of the type we have just seen for Mars, or even nuclear electric thrusters are not enough for this task. But nuclear fusion thrusters are at the limit. Now, nuclear fusion thrusters seems to be not so far from realization. There is the University of Princeton that is working on that, and there is a company in England that says that they are well advanced in experimentation. So they have a higher ejection velocity, which are still not enough for what is needed for interstellar travel. But we can think that the second generation of these thrusters may be enough. Now we know that there are many extrasolar terrestrial planets. They are constantly being discovered, and they are not so far from Earth. That is, the nearest stars have extrasolar terrestrial extrasolar planets. Here we have a list, for example, Proxima Centauri, that is the closest star, has a planet whose mass is 1.07 Earth. The radius is just like the one of Earth. The temperature is a bit low, but much higher than Mars, for example. And there are many others. For example, there are even planets that are higher temperature. For example, 43 degrees should be good. And some of them are locked in a rotation around the star, but so the habitable zone is very small, but others not. About all these lists, we can say that the most interesting ones are those at about 11 light years. But for the first attempt, the idea of Proxima Centauri b would be a viable possibility. Okay, when one thinks about going to other stars, we think that we are limited by the relativity speed limit. This joke is classic. But the point is not that. The point is that the huge quantities of energy needed to go not at the speed of light, which is impossible for present physics, but at a small fraction of the speed of light. This means that we need to have a big advance in propulsion. These plots show you the delta V you need to reach in the interstellar cruise a given fraction of the speed of light. You see that after at speed larger than 0.01%, these speeds are in percent of the speed of light. Even only at 0.1% of the speed of light, you see that if you take into account or you don't take into account the energy to leave the solar system, the result is practically the same. That is, all the energy you need is to reach the high speed, not to get out from the solar system. If we are limited, at least until we have some very revolutionary propulsion system, we are limited to a small fraction of the speed of light. It means that the travel lasts tens or even hundreds of years, which means that what you need is what is called a generation ship or a space ark. If we are in that situation, the solution is ark ships or generation ships or hibernation ships, that carry humans hibernated. Then there are a lot of ideas going around, but for example, to carry human embryos frozen and then to wake them and to develop them on their arrival, or so-called emulation ships, that is, ships carrying not true human, but human minds emulated on computers. These three relativistic ships need a lot of energy, which for now we can consider a long-term idea and not an idea in a reasonable time. And these are other two, I would say, that are infeasible for ethical problems. There are ethical problems even for ark ships. For example, to send people on a cruise of 450 years, let's say, or something like that, raises moral questions, because those who live, okay, they have decided to live, but their descendants are locked on a starship and will spend all their life on a starship without having decided it. So there are, even in this case, some ethical problems. But provided that we are a species that is used to live in space, that is, there will be people living in space station for the whole life, these are less problematic. Well, let's assume that in 2190, and this date is
1 minute, Giancarlo, 1 minute.
Thrown there. We have the thrusters. We can, the idea of at the end of the next century is because you need to launch before probes that make a flyby, then probes that go around the planet, because you need to know exactly how is the planet. And this is the idea of the Starship. This is a Starship that can carry 330 people. You will send a flotilla of 3 of these starships, because 1,000 people is enough for genetic variety and so on, and it's possible. And we'll have a volume of, well, let's stay with the mass, a mass of, a total mass of 555,000 tons. It's huge, enormous. But let's see what we have done. The biggest aircraft carrier now is 104,000 tons. The biggest cruise ship is 2,000 250,000 tons, 250,000 tons. And the biggest supertanker that was built, that is the biggest moving manufacture humankind has built, is heavier than our potential starship. So a starship of this kind, provided that we have the propulsion system, and we have studied interstellar space well enough, is something that is not something enormous we will never build, but is not bigger in mass, it's a bit bigger in length of a big supertanker. Think that there are designs for a cruise ship that is 1.6 kilometers in length and is millions tons in mass. So it is a big thing, but it's not something impossible. This is the idea. These are the tanks. These are the rings that rotating generate centrifugal force to simulate gravitation. And this can reach Alpha Centauri in about 400 years, carrying in 3 starships 1,000 people that can start a colony, the first colony outside the solar system. This can be launched if technology goes on like is hoped in about 200 years. So we can answer yes to the first question, that is it possible? Yes. And when it can be done, let's say 200 years. And with this, I close. Thank you very much.
Thank you very much, Giancarlo. This is a real look in the future, but it is not just science fiction. This is something that is feasible.
Yes, it's not science fiction. It's something that it will become feasible in about 200 years. Less, I don't think so.
For sure, yes. Any question, any comment? Maya?
Of course, Giancarlo, 400 years means several generations.
Yes.
Inside the ark. So you need to provide education, you need to provide everything.
Yes. The point,
it's a word. It's a word.
It's a word.
Yeah.
The 1,000 people is for 2 reasons. First, the genetic variety to have a feasible, let's say, descent. And second, the variety of competencies, because you need all type of competencies to go on with civilization, because it's not only a word, it's a civilization that moves.
Yeah, definitely. Very interesting.
But there are many papers around that can be easily found on the minimum number of people that can go.
Yeah. Probably they will grow also.
Well, no, the point, one of the ethical point is that you need a very strict birth control, because until you reach your destination, you cannot grow, because you don't have the space to cultivate food for everybody.
Yeah, sure.
Okay.
If I may.
Amazing.
There was this really cool project called Project Hyperion to investigate the different designs for interstellar ships. I think this is worth checking out. There's also the Ecolance by Robert Ansman. That's one of my big favorites. I'll drop a link in the chat if you guys would like to check out a video essay about either two of these projects. Thanks.
Yes, there are many projects, and all are based on very advanced propulsion. But I hope that nuclear fusion will be available, and much earlier than the 200 years. It's all the other things that we don't have.
I mean, we are very close to pulse fusion. The issue seems to be we've maintained a continuous fusion reaction, if I'm not mistaken.
No, it's possible to maintain a continuous fusion reaction because this is a sort of thermal engine, and this that expels heat with the propellant that is the same hydrogen that undergoes the fusion reaction. That is deuterium, some helium-3, and a lot of hydrogen in such a way that the ejection velocity is not too high. And magnetic confinement is possible because there is a continuous change of the nuclear fuel. And so the idea of the direct fusion drive, DFD, that is developed in Princeton. Well, I sent 2 students to do the thesis on that in Princeton, and they said that before 2030, they hope to have the DFD tested in space. I don't think that they are able to do that, but they are not so far from building it. They are already experimenting.
Very interesting, because yes, one of the big problems of nuclear fusion is that the part of course of confinement, but mixing propulsion and nuclear fusion, I think, gives a lot of advantages.
Yes, yes, because while if you make nuclear fusion to produce electricity, you have always your fusion mass there. In propulsion, you throw away the very hot fusion material, and so this makes it easier than to produce electricity, because fusion, you can also do nuclear fusion to produce electricity and then electric propulsion. But this is not easier, is more difficult.
Yeah, it is, yes, for sure. Okay. Aziz, you have a question?
Yes, please. The population is exactly correct to be from 500 to 1,000, because this can have the genetic diversity. But the question is how they are going to be living 200 years. Okay, are they going to be sleeping cryogenically all of that time?
No. There is the possibility of not cryogenically sleeping, but hibernation, which is done in a different way, because it's like the hibernation of bears and squirrels. That is hormones that cause hibernation. This is well advanced, the study, but I'm not sure that hibernation can work for interstellar. It can work very well for going to Mars, because if you are hibernated, you don't suffer from radiation, and so that's a big advantage. But for so many years, I don't think that hibernation will be feasible in a reasonable time. The point is that generation after generation, people is born and dies, as every people, and live all their life in this artificial environment. There are many, in fact, it's called a generation ship, because there are several generations, one after the other. It will be the 8th or 9th generation that arrives.
So there will be like a time capsule.
Yeah.
When they are awake, okay, everything has changed. Okay, all the perspective, all of the things. That will be interesting. Thank you.
Okay.
Okay, thank you very much. I think we have spent a lot of time on this, but it's very
Yes.
interesting. It's a very, very, very good topic. And then, but now we have to move to the next presentation by Gayatri Sridhar Hedge. Are you here? Gayatri?
I'm afraid not. Let me check, but no, she's not here.
She's not here, so we have we may skip if waiting for her. We can skip to the next one. We already had Patrick Collins, so we can skip to Niklas Järvstråt. I don't know if I pronounced correctly.
Yeah, very good. Thank you.
Okay, so are you from Sweden?
I am in Sweden, indeed. Yes.
Yeah.
And let's see if I can share my screen.
So please, the floor is yours.
There. That should be my screen.
Yes.
Yes. Okay.
Oh, hello. My name is Niklas Järvstråt, and I'm shooting a bit higher than most people on this conference, with the possible exception of Professor Genta, which is a similar level of generation ships. I will be presenting two roads to interstellar expansion, one direct towards the center of the galaxy, and one that I called the Orion arm strategy. The question is, how do we settle the galaxy? Not just the nearest star. We need to take a bit bigger grip, I think. So how should humanity expand into the galaxy? I see two main natural choices looking at the galactic map. This is a little section of the Milky Way. And we have one, which the direct route, you just take the course directly to the center. Of course, there are no stars directly, so it will be a rather winding route, regardless of which one you do. And the second one, Route B, then you follow what is called the Orion arm, which is a slightly denser organization of stars. And then you attach to the bar in the middle towards the galactic center. And once you get here, you can then decide whether the galactic center is actually a place you want to go to, which may or may not be the case. So we have two cases, Route A, the B line, and Route B, the scenic route. The problem in deciding the route is that the step length will drive costs. And it's not linear, it's very non-linear. And I'll get back to that. One kind of bike condition is shielding. You can't go too fast because then the shielding mass will increase, and that rises very steeply with cruise speed. So even if you would like to go faster, that drives up the mass. So you have to bring along more reaction mass and more fuel. The other two is recycling. I'm talking generation ships, as the previous speaker. So we have to recycle everything very much. I'm not thinking hibernation. I've not looked into that. And recycling, we're pretty poor at doing that now. If we get 90%, they're happy, but that's 90% per year. And if we have 90% per year and want to be going for 400 years, then that is it's completely prohibitive. It needs to be within fractions of a percent that is not recycled every year. We also discussed briefly population expansion. I do think that allowing the population to expand during the trip is not only a pragmatic but also an ethical way of handling it. We have had experiments on Earth of reducing the population expansion, and China is still struggling to get back into a decent level of population, to positive population expansion. So the conclusion here, because both recycling effects and population is exponentially increasing, it's not, we don't need to minimize we should minimize the worst leg, not the average distance. So one route has, apart from being much longer if galactic center is where we're heading, one of these two routes has hubs or clusters of stars. The other has reduction in star density. So there's more dense regions if you follow the Orion arm. And if you go direct to the center, it leaves the arm within less than 500 light years, and there's no cataloged hub for at least 10,000 light years. If you follow the Orion arm, then there are two within 5,000 light years. There are two quite big clusters. The mean spacing differs by just 3%. It does make a difference, but it's not that much. The wind is not spacing, though. It is the clusters. So I have also been downloading a star map and try to look at what does it look if we go in one direction or the other. And let me see, I should be able to give you a live. So this is a simulation where I have got in 90 degrees. The Orion arm is at 80 degrees. So here I get in, let's see, if we remove the waypoints to start with. That's there. There's two ways of calculating in order to get as far in this direction as possible. One is the greedy algorithm, so you just pick one, the closest star within a cone, and one is a min-max algorithm. And if you take the one where you pick one star along the one line, then you get, after 20 steps, you have reached 124 light years. If we instead go towards the center, then that was the same scale. Then you have reached that one, 75 light years. So it makes a lot of a difference. And the lowest step is 6.7 light years going that direction, and it was 6.2. No, wait. It's 6.5 if you go in the other direction. This is a live simulation, so you can zoom and turn it around and see what stars are being used. And that is also part of the output. Inside each of these clusters, two within 5,000 light years, the separation between stars is about 1 light year. So it's much easier to get a lot of real estate at a very low cost, because, well, 1 light year is not very low cost current launch standard, but it's way cheaper than 5 light years. And within the nearest one, it's about 10,000 settlable systems. And within the next one at 5,000 light years, it's bigger, so it's around 100,000. And the background field is roughly 7 light year apart. Now, settlable system is something that I have introduced because there's a lot of talk about habitable zone. But with habitable zone, we mean where there can be liquid water. And that's not really needed in order to settle the system. You need water and volatiles, but they don't need to be liquid. You need energy to make them liquid. My idea is that sending embryos is a logistic advantage. It is not necessary, but this tiny one, that's the one that Professor Genta talked about. But with the addition of an embryo bank, we need to have then a couple of hundred people going to make sure that the ship actually arrives. The alternative is to have maybe 1,000, 10,000 times as big ship where you have live crew. And then you start with the ship not being full and make sure it gets full. My argument on ethic is that no unborn child ever consents, not here, not on a ship. Parents have always decided where a child's life begins. Moving to America doesn't mean that it's unethical to bear children later. The alternative version decides too as well. If you send volunteers, they have their children mid-voyage who never consented either. So the choice isn't ethical, it's logistical.
Your time is over.
Yep. So I am trying to start building this generation ship in an old school building in the north of Sweden. I do it by working on the closed loop system. There is a piece of bedrock in the basement, which I call a mine. I will be manufacturing stuff, calling that factory. I do grow plants, which is a greenhouse. There will be bedrooms, so you can come here and visit. That's the human habitation part of the system. And I'm building an expert advisory panel. There will be quarterly subgroup calls for these 4 sections. Off-site, no travel. If you know a piece of this puzzle, send me a mail. You're welcome. Questions?
Thank you. It's yearly something for the very long future in a way.
Yes.
Yeah, no question. I was kind of hoping to hear what sort of timescale you were hoping to project your galactic trip on. And
yeah, well, Conquering the Galaxy. I have started writing a paper on Conquering the Galaxy in 3,535 easy steps. And then I mean to as a nod to a previous book with a similar name. So about 200,000 years. No, sorry, 200,000 generations, not years. Multiplied by 30 or something.
Terrific. I suppose by that point we'll have like tremendous cultural drift, and a situation like the Theseus ship comes to mind. Like, you know, if it's the same structure but not the same people or the same components, is it still the same project, so to speak?
Indeed, I have a resting sci-fi project called the Kepler Stream, which is the name of a generation ship, and obviously that is the ship that is the first to reach the other end of the galaxy. And when it reaches the other end of the galaxy, there is not an atom left from what started, but the name is still there.
Good enough.
Of course, yes.
Yeah.
But this is true for everything in the end, because even our body is constantly changing, and no single atom of our body was present when we were born, probably.
Yes. A huge challenge for that kind of civilization to span the galaxy is, of course, to communicate. It takes 200,000 years for a radio signal to go from one end of the galaxy to the other end and back.
I'd be using quantum entanglement because any other approach is not going to work.
If that works, I doubt it, but we'll see. Well, I probably will not, but somebody will in the future. There is a hand being raised.
Okay, yes, Aziz, please.
Yes, this is interesting. The question is, it will be about 8 million years. Okay, so humans in their development, okay, evolution in the last 500,000 years. Okay, this is what. So, what kind of being are they're going to be in this 8 million year? Because it's like each generation about 40 years, and doing this simple calculation, it will be 8 million years. So they are going to be different creatures. Okay, so that's very interesting. Thanks.
That is indeed a very good question. I have a kind of hypothesis on that, and I'm extrapolating from starting from hydrogen atom, going via single cell organism and then into human societies. Now we have AI, which could, if everything goes well, knit us together into some kind of superorganism, call it a galactic amoeba, that then become a bigger type of consciousness that we as humans are a part of. Sort of like a neuron in the brain, but more one level up, obviously.
Of course.
But that doesn't influence the generation ship strategy that I'm presenting here, obviously. This is very far speculation.
For sure. Yes. So thank you very much for this sight to the distant future, and then we can move maybe to something nearer. If Margarita Safonova is the next speaker.
Can you
Are
hear
you
me?
here? Okay. She will talk to us about the Artsimovich Railgun for payloads delivery from the moon. That is a very interesting topic also.
Can you hear me?
Yes, yes, we can.
Oh, unfortunately, I don't know why, but my video disappeared, stopped working. So I'll try to share my screen now.
Okay.
Yeah. Is it sharing?
Yes, we can see it.
Okay, now I'll put it in the presentation. Oh, can you see? Can you see my slide?
Yes, yes, good.
So unfortunately, I'm afraid that my talk, comparing to all the previous ones, will be a bit more pragmatic and maybe boring even. But I'll try to do my best. So using Railgun from payload delivery. So what are the ways to leave a planet? Well, Chinese invented rockets. Tsiolkovsky suggested using them to go to space. But what happened is that we on Earth are actually super lucky. Escape speed from the surface of Earth is just around the speed limit attainable by the chemical propulsion. And chemical rocket launches if we had lived on the super Earth, we wouldn't be able to do that. There is a fantastic paper by Hipke. And another way, escape velocity from planets near dwarf stars, like Proxima b, for example, into space, is much higher than ours. It's 42. Ours is 42 kilometers per second. There it will be 65 kilometers per second. So to launch 1 kg, just 1 kg of CubeSat would take 1,000 times more fuel than carried by the space shuttle, which is 1.7 million kilograms of propellant at liftoff. And this is the Loeb's paper. Of course, there is also space elevators, as we had fantastic presentations, several of them for several days. Tsiolkovsky, by the way, suggested to launch payloads to the Earth orbit from the very high towers in a thought experiment. And Alotaibi in the 60s suggested to use a theater. But the problem here, the first problem is the heavy counterweight. Like at 100,000 kilometers, we learned already, for example, 600-ton asteroid. Isn't it a bit too close for safety? There are other problems. Air traffic. Now there is a lot of, in 25, as you can see, the air traffic reached 100 million flights and space launches, LEO satellites, turbulent weather, terrorist threats, of course, space debris, both natural and anthropogenic. Actually, up to 1 million asteroids there are on Earth crossing orbit. And in April 26, man-made track debris estimated as this many object sizes, up to 10 centimeters. Well, there are problems, and then they're going only to be increasing, as you can see from this cartoon. Now, by supposed to be 1.23 million proposed satellites in low Earth orbit. And there are Chinese suggestions. I don't know if you heard about it, but China suggesting up to 200,000 satellites in very low Earth orbit. They already tested it. They said that LEO is too crowded, and they want to occupy now VLEO, very low Earth orbit. And they propose 200,000 and even up to millions of them. Well, as far as satellites are concerned, I firmly believe in this. That if you remember, everyone must have seen Geostorm, and this was Dutch boy, space network, satellite network. Actually, I believe in this. We need that. So for anything that is, we have to go out, even for space astronomy. Then there are electromagnetic launches. These launches essentially use magnetic fields to convert large amounts of stored electric energy into kinetic energy of the projectile. And it consists, as you can see, as a sliding metal conductor armature between two rails towards projectiles. The first idea of a railgun was actually suggested in 1902. And this professor even built 10-meter long electromagnetic gun and launched 10 kg iron projectile at up to 80 meters per second. But he abandoned effort, realizing there are no funds and no available pulse power sources to operate his guns. Well, now they actually exist, and the idea kept on developing in the 1723, 50s. First idea to use this to launch into space was by Arthur C. Clarke. Electromagnetic launching as a major contribution to space flight. Designs, this, for example, McNabb designed this linear using this material, using it high in the mountains to reduce aerothermal heat load on the launch payload, and to place rail in a vacuum tube to reduce friction losses. And another configuration is a circular one with diameter of a few kilometers, and also preferably built high in the mountains, because the main idea is very high acceleration, and it means that very high aerothermal load on the payload. So actually, then there are other propulsion methods like nuclear propulsion, beamed energy propulsion, and the latest fad is air-breathing propulsion. This system utilizes atmospheric oxygen as an oxidizer to burn the fuel, not to carry oxygen with you. Makes rockets significantly lighter, can be used only within the denser layer of Earth atmospheres when there is adequate supply of oxygen, which is another problem compared with along with the chemical propulsion because of pollution. Chemical makeup of the exhaust is CO2, water vapor. Well, this, for example, supersonic ramjet or scramjet, in 23, even India joined it and became the 4th country to successfully demonstrate the flight testing. I'm not aware of a review on a method to leave a planet. And there are several descriptions, of course, but here what I suggest that some of us it would be a great product of this symposium to actually produce a review on all the methods to leave a planet, not space propulsion, to leave a planet, plus the pluses, including the pluses, minuses, and for example, the chemical propulsion, air-breathing propulsion produced a lot of pollution. Electromagnetic launches, okay, but there's a problem with the aerothermal load. Space elevator is very good and by the way, great idea for the moon, but on Earth it is a problem because of exactly because of the traffic and the satellites and so on. So I would be happy to, if somebody will agree with me, and we will jointly write the review on this. Well, Moon avoids some of the terrestrial problems, like high gravity and atmosphere. So for that Relsotron system U-star, which I mentioned, from Earth to Leo, it was estimated that total energy cost would be 44 gigajoules. Most of energy, of course, is spent on taking payload to the launch altitude, overcome atmosphere resistance, and so on. That energy cost of taking just 1 kg payload to Leo is only 24% of the total energy expenditure. Lunar conditions simplify the construction and reduce all the costs, energy included, of such accelerator. The lunar regolith can be a local source of material. The absence of the atmosphere, especially, removes the necessity of a vacuum tube, and there is no need of aerodynamic container and aeroshell. The container protecting the payload from the aerothermal load. So these launches based on the Moon could be used to deliver mined materials to destinations such as Lagrange colonies, Earth or near Earth locations, or proposed NASA Gateway space station in support of Mars or solar system exploration. Once placed on the Moon, such launches could also serve other applications, like defense of lunar colonies against meteorite impact, launches of suborbital
1 minute,
orbital.
Margarita. 1 minute.
Sorry?
1
Okay.
minute.
Yes. So there are 3 possible lunar locations to launch: low lunar orbit, cislunar space, L1 Lagrange point. When we consider 300 kilograms Werner module of this, we calculated everything for this here. And to launch requires 44 GJ on the Moon. So much significant reduction in the construction cost. So it can be built there using local materials. Any necessary equipment from Earth can be brought only once. So this is the reference. We have written the initial proposal. Originally it was published in Russian and then translated and available at this DOI. So now we are writing the bigger paper, expanded. For example, we use lunar libration. So because with the lunar liberation, that things will change a little bit. For example, to reach L1 point with 0 velocity, you have to consider lunar liberation. Okay, thank you for listening.
Thank you very much. I think this presentation goes into the direction we are following, because also Gerard O'Neill, of course, proposed the lunar Railgun type launch for the reasons that you explained very well, of course.
I'm just trying
Thank you.
I'm trying to disconnect. Sorry.
Please, Frank, you have a question?
Yes, I would, for the Railgun strategy for setting payloads, because basically you get the energy to send it all the way up to high into it's not quite the orbit. You have to raise the the perihelion for that to be done. So like, what type of strategy is going to be used for circularization burn for achieving said orbit? Are we talking is through solids or something important?
Can you disconnect me? I don't know what happened, but my computer refuses to stop screen.
Yes, I was wondering for the lunar railgun, what type of strategy
Yes, yes. So
circularization.
that would be great. If you can, I would be happy to. If you want to write with us, I will be happy to collaborate about it because we're still writing the expanded paper.
Because I experienced a few options like ISRU. It's just most of them are going to be based off like aluminum powders and like oxygen, so like solids essentially. But like O'Neill suggested, like a big like net to catch it in orbit too. That's another approach I'd really like to explore if other people have come up with for ways to do that without using too much material.
Yes, I think that O'Neill's ideas are the starting point about this.
Absolutely.
Yeah. If you can write to me, my email is simply available. I would be happy to discuss this.
Terrific. Looking forward to that.
Yes, yes, absolutely. And especially, I would be really happy if we really produce a review on ways to live a planet.
Like a full compendium.
What are the ways to live a planet? What are the pluses, minuses of each method? That would be amazing review. Especially coming from SRI.
Yeah. Okay. Okay, thank you for talking about this other important topic. And then I think we can move to the last presentation of the session. If Gregory Harrison is available, are you here?
Yes.
Gregory, so this is about electric space thrusters for single stage of space, and so another interesting topic for the future.
Hi, I'm Gregory Harrison, Gravitronics. I'd like to talk with you about this progress on our electric space thruster that has multi-domain applicability. I'd like to tell you why it's a good thing, what it does, how it works, and if it works, what benefits you'll receive from it. So the idea here is it's a completely electric rocket. There's no chemical fuel. It's non-explosive and carry massive payloads. You can large populations can leave the Earth at once. Here, the big picture here is an ionic rocket with the ion producing light at the front and then recombining at the back, showing rocket moving through space. It can enhance humanity's expansion across the cislunar, the solar civilizations, and other stars. So going on, here is how it works. It works like an inverted mass driver. Back in the 1980s, I met with Dr. Gerard K. O'Neill, and he had offered to work with me on mass driver, and I did build a mass driver, but this is like an inverted mass driver because the mass driver will send masses off a planet, let's say, where it stays in one place. But in this case, we're using the mass of the ions to pull against, and we move the mass driver, which is the rocket in this case. On the upper left is an ion cloud, which we create using an ionizer, and then it is pulled on with these using the Coulomb forces with electrodes that are driven by electrode drivers, and that is one thing that would be electrostatic, but this is electrodynamic. If you look on the left, you see that there's levels of these electrodes. There's a positive and negative. There's a dipole right now. You can have other configurations, but this was the cheapest way to get started, in my opinion. They're labeled as L0, L level 1, in remembrance of the Lagrangian points in the L5 society. So here is what happens is you start. Let me show you a picture of it running on an FPGA card where these different levels of dipoles fire, and then the next level fires, and the next level fires and pulls the ions back pulls the engine against the ions as if it was an aeroplane with a propeller, or like a canoe in water. You don't bring along any hydrogen. You don't bring anything. There's hydrogen throughout the galaxy. There's hydrogen in the Earth atmosphere, of course, and so it can be built by anyone. One trick is to using high voltage to charge the electrodes, and that's where we're at right now. But looking through the math and the physics, it became such that it produces a tremendous amount of thrust. And it was calculated to produce 29 zettanewtons for a 1 meter rocket, which is a quadrillion times more than the Saturn V rocket produced. And if you just limit it to 1G, you can get to Mars in 1.7 to 6 days. You can get to the moon in under an hour. Nearest stars in 10 years, less than 10 years. That's added this galactic, because you can pretty much get to anywhere in the galaxy in about 10 years, departing from any problems with superluminal transport, because this is ponderous matter. It's not light. But anyway, that's something to be seen in the future, whether it can or not. But also you get a fast, low radiation dose, and depends on how fast you move the fluent, which is what I call it, the fluent down the engine. You can perhaps get relativistic speeds with respect to the ion cloud at the front, so that you can increase the mass of the ions that you're pulling against, and get more momentum that way. And then also, depending on your speed, it may be hard to continue to have a higher speed fluent than the ion cloud, in which case you'd have to warp the engine. And that way you would skip levels of electrodes just for your electronics to keep up, because it's moving so fast. So that's an engine warp at high speed. Let's go on. Here is where we're at now. Because it's so the immense amount of capability, I had to make one, because it seemed like it would be remiss to not, because you have to have some kind of prototype to see if anything will happen at all. So here we're at now. The hard part is these ECD, which is the electrode charging driver. Everything else you can get off the shelf. You could buy these electrodes. These are half spherical copper electrodes. They go on the engine tube. It's going to be suspended by some non-metallic cables, and then the electrode charging drivers accept the pulses from this new FPGA card, which is a zinc card, lets you modify things at the picosecond level, so you can have great simultaneity between different electrodes, and you could tune them to produce the correct fluent going down the engine. And so this will be housed in an Alexan bird cage with the electro charging drivers hanging on the side of the cage, or mounted on the side of the cage. You'll be able to measure acceleration with an accelerometer on there. There's an ionizer ready to go. The laser time of flight sensor will see if it produces thrust. It'll move the engine tube, and you'll see that there's a difference in the distance between this edge and the engine. So the hard part was to produce the electrode charging drivers, and that's where we're at now. I've been breadboarded. It works at 60 volts. Now I'm producing a board to run at 1500 volts, which is it's taken a lot longer than I was hoping, but it's a lot of issues with having a hybrid board that takes LVDS, you plug an Ethernet cable into it from the fluent generator here, and that goes and causes the 1500 volts to hit the electrodes, and then in sequence. So there's a lot of different ways you can sequence these. You can use thrust vector control. You can have multiple different sizes, different levels of electrode. I figure that when this thing really gets moving, if it does, that a lot of people can build this in their garage anywhere, and you can experiment, and there'll be a lot of great engineering to be done, just as if there was the beginning of the automotive epic in human life. So here's some applications. I call it an H drive. It's sometimes because of the H bridge configuration for the electrode drivers. Anyway, that's all. If you had this thing running, you can hook up to asteroids. You can pull them away. You can, at the speed you can push these things with the massive thrust, it would send them right out of the universe, not universe, but the solar system. Or you can grab them and mine them. You can have this thing as reusable, so it can fly around and start picking up debris everywhere in outer space. So here on terrestrial applications, you can have a little, you can put a seat on this thing and have it fly you around. That's a happy thought for me, but you can use it to lift things, to fly terrestrially. In the GEO-Lunar system, of course, you can fly between the Earth and the Moon. And if you're doing that in under an hour, that's a great thought. Space tourism, certainly you can fly to Mars with the people flying, watching through the windows. Then if you, in deep space, since this could reach another star in 10 years at 1G, I mean, if you want to go at higher Gs, you could get there a lot faster. But at 1G, a human could survive that in 10 years to Alpha Centauri. Basically, hydrogen, borrowing a concept from the Bussard ramjet, you can have hydrogen pulling in. And because you're pulling on it, it doesn't matter about pushing it out the back, since that's not how this is moving ahead. You're pulling on the momentum of hydrogen. You can capture that hydrogen and reuse it, perhaps, on the flight to the world, another world.
Time is over.
Yes, sir. And
sorry.
Thank you. That's it. And hopefully we'll have something by the end of the year. We'll see.
Okay, but one thing I wanted to ask, but ion thrusters do exist and they are very much used nowadays because I think you have thousands of ion thrusters already in space because each Starlink satellite has a ion thruster. So
right,
I don't understand because I'm not an expert of ion thruster technology, but they are well known. They have been used for years, and their characteristics, as far as I know, is that they have very high efficiency and very high specific impulse, but very low thrust.
Right. This is just the opposite. It has a high ISP, 600 years if you're using a nuclear generator to create the electricity. But the thrust is massive on this. It's capable of lifting off the planet Earth if it works. So that's why we're making this proof of concept prototype to see if fluent propulsion is a viable thing. I am familiar with all the other ions. They use electrostatic methods to thrust ions out the back, and using them as a force, a Newton F equals ma type acceleration. But this is using the Coulomb acceleration from the mass, the momentum of the ions that are existing, and it's been calculated. The math works, but we'll have to see if it does anything.
Joe, yeah.
I'd like to know where the hydrogen comes from and where the electricity comes from.
Well, electricity, of course, you have any method of creating that nuclear generator or whatever. The ions are in the atmosphere, and you ionize the atmospheric hydrogen or atmospheric whatever molecules you want that then are acted upon by the electrodes, pulling the engine toward using the momentum of the atomic hydrogen.
But if you're going to star systems, there aren't atmosphere to draw the hydrogen from.
There is hydrogen throughout the galaxy, There is, and it was calculated to be sufficient. And if you're using the relativistic increase of the momentum of the hydrogen atom, that's even better. But there is sufficient hydrogen throughout the galaxy to use as thrust, not thrust, but to pull on. If you could use the Bussard ramjet to pull in more hydrogen, that technology has been discussed, but I don't think you need that in this case.
But in other words, you would need something like a compact fusion to really make.
It would make sense to have some kind of good electrical generating system. Between the Earth and Mars, you could possibly store it in batteries, but there's no free lunch. So you probably need a good bit of electricity when this thing moves.
To get zenonewtons, I think you really would need a compact nuclear fusion.
Right. That's a high level. That was 1 cubic meter of hydrogen fully ionized with the density available on Earth for that. So there's hopefully there'll be some result, but that was using the best physics I could come up with to calculate that massive.
Well, good. I hope there's some sort of publication on your work.
Yeah, it's on researchnet.org. It was published at the AIAA conference Ascend in 2025. So there's a few things
Niklas, have you some comment?
So you find a hydrogen atom and you accelerate it. So you need to let it out backwards as well.
No, the acceleration does occur. We're pulling on a stationary hydrogen atom. So you try to pull on it faster than the mean free space travel of a hydrogen atom. So you're pulling on the momentum of the hydrogen atom with pulling the ship forward. Whether it goes out the back, that would be another issue. That why you may be able to grab the hydrogen that exhausts out the back after you've pulled on it.
You need to let it out on the back, because otherwise you keep it with you, and then you have bring the momentum back up in a forward motion. So then you would not have lost the momentum gain.
Yeah, but you don't need that hydrogen atom once you've used it. It could go out the back, or you could grab it.
Hydrogen atoms are good to have, so you would have wanted them, but yeah, it's better in this case to use it as fuel. Yep, gotcha.
Okay, I think we have reached the end of this session. So maybe today we are a little late again. So
yes,
we had plenty of discussion anyway for each presentation. So I think what you say, Adriano, we can move to the next session. And Werner, if you want to have a final comment.
Werner.
Thank you very much.
Yes, I would thank everyone who has taken part of this discussion, and it was very, very interesting. And I have also learned much more details about space technology this afternoon. I thank you everyone to have joined us. Thank you very much, and bye-bye.
Thank you, Werner. Thank you, everybody, for presenting your fantastic, very, very interesting papers. And before we go to the next panel, I would ask everybody, because we still have about 40 people connected, to switch on their cameras so we can take a screenshot of our whole assembly. Okay, I will go to gallery. Yeah, come on. Everybody, switch on your cameras. Yeah, I see someone more not switched on. Okay, wait a little bit more for everybody to switch on. Okay. Okay. Someone more? Daring Trife, Aldo Velasquez. Guling, where are you, Guling? Show up, please. Okay, she's not ready. Okay, I will start to take a screenshot now. Taken, then let me paste it somewhere. Beautiful picture, beautiful. We have a very, very nice community here. Okay. Oh, I have 2 pages. Sorry, give me a few seconds to save what we made, otherwise it is useless. Just a moment. Okay. Now there's something I don't understand, because before I was seeing 2 pages, now 1 page only. Who knows how Zoom is thinking? Because now we must be prepared that all the things we use are thinking. Yeah, okay. And it's a joke because since I am an old softwareist, I made software my whole life. Always the software people used to personalize their creators, let me say, their programs, their piece of software, and so on. But now it is real. Now we have these things that are really thinking. Okay, I believe we can go back to our program. So I think Joe Pelton is the chair of the next panel.
Results for the
Are you ready?
targets I showed in order of how I showed them. But yeah, that's basically it. And the further goals of my project would be to compare the joint fit results with single region fits.
I'm sorry.
And also by excluding the UV lines, quantifier.
Who is talking in the background?
Anyway, let's start the next panel. We have a very diverse, interesting group to discuss the topic of radiation dangers and how could we invest in the future to cope with the danger of cosmic radiation. And we have experts from around the world. I think we will be discussing first the idea of passive protection systems that can be used in outer space. And in this case, what we use in dentist offices doesn't really work that well in outer space because cosmic radiation and lead shielding don't necessarily produce the results that we would want because you could have a possible nuclear reaction with high enough energy levels. The other discussion is one that Jim Green and I have been actually addressing, which is the idea, can you create magnetic shielding systems to protect from radiation? And could you even create a magnetic shielding system for Mars to actually create terraforming and atmosphere that could really protect people living on Mars? And so the question is where and how to invest. I would just like to add another topic. I'm hoping that maybe Tommaso Segoba of the International Association for the Advancement of Space Safety might address, and that is, do we have the right institutional structure in place to help us not only with radiation standards and protective systems for private space stations, where currently NASA has basically said we're going to take over the role of regulatory safety for private space stations and authorizing them. This is something that NASA is really not well equipped for, and I think Tommaso maybe actually can note all the different things that an International Space Safety Institute could address in terms of getting agreed international standards on a whole host of safety issues to address maybe even issues of space debris and how that could be addressed, and of course radiation standards and how you authorize them for commercial space stations. So with that introduction, I'm going to turn it to our moderator, Adriano. I think you're going to address our various speakers. And I think starting...
yes. So thank you very much, Joe, for your first introduction. On this panel, we will have Joe Pelton, is Dean Emeritus of the ISU, International Space University, and also the President of ACES worldwide. Then we have Alessandro Bartoloni. He is a researcher and AMAS team leader at CERN in Geneva and in INFN in Rome. Then we have James Green, former chief scientist at NASA. We have Tommaso Sgobba, the president and founder of the International Association for the Advancement of Space Safety, and myself, the founder and CEO of SRI. So the idea of this panel was to make a cultural provocation, because we made a quick research that shows that the research, the scientific research for life protection and health protection in space is very, very underfunded. What we have found, that could be wrong because, you know, artificial intelligence is not that accurate when give you the data. However, we found that there are around 200 million globally in the world invested on this research. That's nothing considered to the billions that are spent on other subjects. So a logical question rise up to our mind. What could we do? What could the research do if we had at least 10,000 more financing? Let's say 2 billion a year. What could we do? Could we accelerate the results of the research for passive and active protections against radiations? And also the other point that's very, very urgent, start working with simulated gravity in creating first demonstrator of orbital simulated gravity stations. So this is the basic question of this panel. We have invited some of the best experts in this field, Professor Alessandro Bartoloni, Professor Thomas Sgobba, Joe Pelton, and Jim Green. And okay. Now, I think we maybe, Joe, you will go ahead making some questions to our panelists and making a round answers or something like that. It's up to you.
Well, I would like to start with Alessandro and ask him, where are we with passive systems to protect astronauts and people who would travel into space? Where are the gaps and where are the opportunities? And particularly progress are being made with water storage systems to make them actually into radiation protection capabilities. So Alessandro, what are your thoughts on that?
Thank you very much, Joseph. Okay, if you agree, I can share some slide with my point of view about this provocative question, or just go into the passive point. For the passive point, let me say that the passive protection is maybe one of the most studied kind of protection, because since the very beginning, it was clear that passive protection is maybe something that we can test, that we can very easily translate from the experience that are used in many different working scenarios in the Earth, starting from nuclear plant, from hospital, let me say from every site in which, since the starting of this adventure of ionizing radiation, that has its origin at the beginning of the last century with the first Marie Curie experiment, protection was one of the things that step by step was clear that was crucial to have the possibility to use the ionizing radiation safely on Earth. And of course, this passive protection that essentially means to use different materials and have the possibility to essentially characterize the material in function of the different kind of radiation that could be exposed during our activities was developed since that time. A very big step in this kind of study happens, of course, during the Second World War, because everyone knows about the Manhattan Project. The Manhattan Project was something that changed completely the scenario in which kind of field, in this kind of field. It was apart the political and civil aspect, of course, from a scientific point of view, was an effort that essentially never was done in the scientific world. And most of the information, most of the techniques that are used to simulate and to characterize the material for passive comes the origin from there. And there was developed taking different fields that essentially are not only about the use of radiation in nuclear plant for nuclear energy, but also for medical purposes. Of course, the space is a completely different scenario. This is, let me say, the final point of my this first my answer to your question.
Sorry, Alessandro. One question.
Yeah.
Did you want to present some slides?
If you want, yes. I think that the format was changed.
But we also don't see you. Maybe your camera is not.
Yes, because just after the photo, the camera stopped. So if you want, I can share my slide. I'm very happy to do.
Yeah, if you think it can help to understand.
Yeah, because it's
Okay.
my...
Before you present slide, I want to correct. You have also to use real facts. Adrian, you mentioned $100 million of research on protection of life. In fact, the whole human spaceflight program is addressing this issue. So these are billions of dollars we are spending in a low Earth orbit and also in deep space. We had also some experiment already on Artemis 1. We had some mock-up of astronaut, and we had sensors measuring what was the effect of radiation. And also in the last Artemis 2 and the next mission, we have a lot of attention, and in terms of hardware and experiment, where we monitor also strategy for reduction of radiation exposure of human being and also other form of life. So don't believe in everything you see with your AI agent. Thank you.
No, but yeah, okay. But however, yeah, later we will discuss. Let's Alessandro to go ahead.
Yes, okay. So the origin was this provocative question, because of course it is clear to everyone that since the Apollo missions, the problem of radiation was faced, was always taken in consideration up to the last Artemis 2 mission. But for the future, the deep space exploration, if I have to reply the provocative question, of course, is not today to launch a specific operational program, but as a way to think about potential direction. So my starting point in that sense is simple. For human exploration beyond the lower Earth orbit is something that will happen for the first time in these days. life protection in space should not be treated as a late safety add-on. It should become one of the organizing principles of exploration architecture. Let me say, when I say in this presentation, the title is From Radiation Monitoring to Human Risk Intelligence, I mean a transition from measuring the environment to understanding what the environment means for the crew, for the habitat, and for mission decision. This is why I put together these three words on this slide: radiation field, biological response, and mission decision. The key issue is the connection among them. We know a lot about each piece, but the challenge is to make them work together in a way that supports real exploration decision. Essentially, the funding gap is not only a question of absolute money. Money is not all. There's no miracle research. It's also a problem for me about fragmentation. If I have to, let me say, suggest a direction for the future, is try to fill this gap of the fragmentation of the different problems. Physics, dosimetry, radiobiology, medicine, habitat engineering, and mission operation often advance in parallel, with excellent work in each community, but with too few mechanisms to close the loop. So essentially, today I will try in a provocative way reframe the question. The classical question is, how do we shield astronauts? That, of course, remains essential. It is, let me say, phased in the right manner also in the today mission, like Artemis 2, 1, and in the future. But for long duration mission, for the real, let me say, multiplanetary civilization, the broader question is, how do we predict, monitor, and manage human risk across the mission? This is not mean as a full project proposal, it's a direction, let me say. And so a tenfold funding scenario could allow us to move from fragmented excellence to a more integrated space health protection agenda. The objective would not be only more papers and not more shielding, or only more shielding concept, but to share capability, better environmental data, better dose models, better biological evidence, better Earth monitoring, and better operational rules. This is what's very important. For example, in an interview that I heard from Luca Parmitano, that was done 2 or 3 days ago about their Artemis 3 mission, he commented that the most of the work that they will do in the near future to create a new procedure that never was done for space mission. And this is also the operational rule or procedure is a very important point. So just to, let me say, organize the discussion, we can think about 5 directions. First, a moon to Mars radiation that risk infrastructure, not just detector, but a coherent chain from the space radiation environment to organ dose and mission scenario. Second, a translational space radiobiology effort. Space radiation is a unique stressor. What I said before is not comparable to what is we face on the Earth, but it also became a frontiers laboratory for radiation biology, oncology, radiotherapy, and radiation protection on Earth. This is, for me, a very important problem. Always try to understand how space, the investigation space, will be used to improve our knowledge of things in general on the Earth. Third, validated digital human twins. This is a sort, let me say, of very diffuse keyword, but let me say that it's very powerful because the human in this case, because we are talking about astronauts or space workers, are models that are able to evolve with the mission. They live with the mission. It's something completely new. And of course, they should make part of this kind of research as they becoming part of this kind of research on the Earth, on radiotherapy, oncology, many other, let me say, medicine fields. So this is very, very important things. Fourth, autonomous monitoring and early warning. On the moon or the way to Mars, the crew cannot depend on immediate terrestrial support. This is something that will happen for the first time. On the ISS, the astronauts are in continuous, let me say, communication with the Earth, with the mission control room. But for Mars or traveling to Mars, it will become completely different. Fifth, demonstrator and shared standards. This is also another important thing that in this kind of there is no need to say again, but it's important that the space exploration will be inspired by sharing knowledge between different space agencies and inside the community. And this could be also the objective of this kind of 10 times funding scheme. Just to create some connection with something that is happening in the real days, because of course there's a lot of people that are doing this kind of research. This is a piece of, let me say, a part of the NASA Moon-Based Architecture User Guide, that of course one of the problems of the ignition program is the habitation system. And in that sense, let me say that the important point today is not, I'm not saying let's us design the habitat, because of course this is done by the other institution. But essentially, the idea is to try to understand that once a habitat is designed to be technically habitable, how do we make it human risk informant? For example, the habitation gaps mention short duration and months plus pressurized habitation. This is something that should be, now you know, this kind of user guide presents some knowledge gap and technological gap. In that sense, this kind of, let me say, direction will be aligned to fill the gap that are also indicated in this kind of user guide. And also many other topics that are, let me say, faced by this user guide, like, for example, the waste and close environment health risk, operations and crew performance, essentially could be addressed in this kind of approach. So essentially, let me say, the message in this panel could be that ignition technology should not only be technically habitable, they should progressively become human risk informed. And this should be done not as a later add-on, but something from the very beginning. And this is a useful example of now, let me say, a provocative funding scenario can be translated into a strategic direction rather than into a rigid operational program. Essentially, this is the pipeline that I could have in mind, that it starts with the space environment, that we say the galactic cosmic rays, solar energetic particles, secondary particle, and the specific surface condition on the Moon and Mars. So this is essentially the topic from which I come from with the MS. Then, of course, we need also transport and those modeling, like, for example, Monte Carlo simulation, habitat geometry, shielding material, organ dose, and also effect on electronic and sensor. The next step, of course, is biology and biomarkers. That means DNA damage and repair, immune response, all the effect at different levels, cardiovascular, central nervous systems, endpoints, cancer, and long-term effect. This is where space radiobiology becomes central. Then comes to the scene, the digital human twin. I repeat, this is very, very important. It's not a slogan. I understand that in these days, digital twin is a very diffuse word. But in the field of the medicine, is entering in the everyday operation due to the capability to this kind of modeling to not be something that is, let me say, fixed. They evolve, they live with the mission. And imagine how much is important to have models that live with the space mission, where we know that the space mission of the future will be always more and more isolated from the Earth. So they will become some, let me say, crucial tools. Finally, the pipeline must end in operational decision. This is important because having a tool in which give us the possibility to the crews to take a quick decision on how to manage a different situation in AVA, in emergency sheltering, in medical support. This will be a mission rule that will be very, very important. Finally, it's also, let me say, the point that this kind of approach could be create the synergy that everyone expects when study the space mission, the future of the space exploration, the capability that understanding our future in the space, we was able to improve our quality of life on the Earth. I will conclude with this final slide that essentially what can be the success of this kind of operation. Of course, try to have this spread this kind of spirit. And essentially, the take-home message from my side is that this provocative tenfold funding scenario could allow us to treat life protection in space as a strategic infrastructure for the Moon to Mars pathway, and to also create a translational laboratory for Earth on Earth. I think that I take all my time. Thank you very much for the attention. And
Thank you very much, Alessandro. So let's turn now to the discussion of whether active systems could actually work. That the idea that maybe magnetic shielding systems that could work locally on the Moon and on Mars as a first step, but as a pathway to possibly being able to create atmospheres on the Moon and, well, much more likely Mars, by having a containment system that could allow the eventually creating of an atmosphere on Mars, which would be the ultimate protective system like we have here on Earth. So Jim, can you enlighten us about what could be done and how hard this might be?
All right, thank you very much, Joe. Let me share my screen, and I'll go to... So do you see one screen?
Yes.
All right, wonderful. So indeed, research now is going on, and this is primarily, of course, done in computers and supercomputers about how to be able to provide artificial magnetospheres. And we're going to talk specifically about Mars in this particular example, and we'll talk about some of the problems that are associated with not only the designing system, developing it, but indeed employing it, but the benefits of why we think that these are important approaches to take. The first thing to notice is indeed Mars has no magnetic field, only remnant fields that have been trapped in the rocks. It did indeed have a fairly significant field in its past, but clearly the currents have stopped, and that field has stopped, that dynamo field has stopped. Now this means then that there's no standoff distance that's created between the planet's atmosphere and the solar wind as we have here on Earth. On the right panel, we see what the current situation is. We see some of the remnant fields are trying to protect certain areas, but very localized. And we see the solar wind coming in and interacting with the ionosphere of the planet itself. This generates a current, that current generates a field, and that field is what is used, induced field is what is used to divert the solar wind course and its magnetic field that it's carrying around the planet. Simulations on this environment are shown in the left-hand panel. Here, this is the one panel we see in the sub-panel we see in the upper left-hand corner is actually data from the MAVEN spacecraft, where we see plumes of atmosphere being pulled out. This is during normal solar wind times. This is on the average of about a kilogram or so a second of oxygen in particular is leaving the planet. And so we see from the particular simulation that this interaction it goes on all the time. Now, of course, what happens in not just the steady times, but many of the other times is indeed significant solar storms. These come from flares, but primarily coronal mass ejections are some of our biggest problems. And for Mars, there's a whole series of processes that occur that actually have the planet participate in this atmospheric loss processes. These escape processes are not only thermal, but they're non-thermal. And indeed, having coronal mass ejections hit the planet produces an enormous change. We end up changing the removal process from, as I mentioned, kilogram or so per second to 3,000 times that of oxygen leaves the atmosphere, being pulled out from these Carrington-like events. Now, the Carrington event that we all talk about is only a couple days, but historically, we're finding out these kind of events are occurring all the time. It's almost like there's another cycle in the sun that then creates these that anywhere from 60 to maybe 100 or 120 years, the sun has these extensive coronal mass ejections, which do the stripping. And of course, that has what we believe is significantly reduced the atmosphere on Mars over the last several billion years since it lost its magnetic field. Now, the dominant process, loss process, is actually what is known as a charge exchange, where we see the solar wind coming in. This is the protons coming in, and they first hit the hydrogen corona of Mars. And so the hydrogen corona of Mars actually extends well into space, at least half or one planetary radii. And so the bow shock, that interaction region that actually pushes the solar wind, is actually well within the hydrogen corona. And so that means that a very fast-moving proton can interact with the neutral hydrogen corona, grab an electron, and then go right through the bow shock and right through the induced magnetic field and impact the atmosphere of Mars. Now, that impact in the upper atmosphere then of the solar wind directly penetrating into the atmosphere causes a sputtering activity, which then creates more complication as more and more of this material then is thrown out into space. So conceptually then, we want to be able to create a boundary which pushes this bow shock and magnetopause away from the hydrogen corona. And many of the simulations seem to indicate, and there's all sorts of configurations, but let me show you, I think, what we think the best configuration of these magnetic fields would be. On the left-hand panel, we see a noon-midnight meridian projection where we have 2 of the 4 magnetic field generating systems, which are in Mars' synchronous orbit, generating a dipole-like magnetic fields, then interacting with the solar wind, indeed pushing that bow shock and magnetopause well away from Mars. This, once again, allows us, based on the current direction, to change the direction of that magnetic field that interacts with the solar wind and then actually constantly pushes it away. Now, in addition to that, in that left-hand panel, you can see that the Jeans law, which then allows for normal thermal expansion into space, would escape along magnetic field lines. And now all those magnetic field lines generated in this particular example are closed field lines. And so what happens is these flux tubes fill up, and even the Jeans process then doesn't really participate in losing the atmosphere. So by By not only blocking the solar wind, we actually create a magnetic barrier that surrounds Mars so that as it outgasses, that outgassing doesn't actually escape into space. And this begins a process that has normally been referred to or called as terraforming, where we then change the environment of Mars such that we can provide a habitable environment for humans. As you can see on the right-hand panel, now we're looking down from the northern hemisphere, and we see these 4 major current nodes that are generating these fields. Now, this is going to require a significant current on the order of 1 gigawatt in each of these, depending on how far away you want to create this magnetopause. And that enables then for this closed magnetosphere to indeed be created. Once again, this then starts an opportunity as humans want to be able to live and work in the long-term basis on Mars, several opportunities for what we call terraforming. As humans then go on the planet, they want to do some global warming. There's several techniques on how to do that, including releasing super greenhouse gases. You want to be able to create a biosphere from that, where you might be releasing microbial life, certain types that can withstand these temperatures, emitting oxygen, converting CO2 into oxygen. That then enables the process of generating an ozone. And then the magnetic shield, as humans are starting the process of changing the atmospheric pressure from about 6 or 7 millibars up to maybe 10 times that, maybe 60 millibars, that now ends up reaching certain limits, such as the Armstrong limit, that allows people to be able to live and work on the surface without a spacesuit. It'll still be cold, but now you're actually really changing the environment. Now, these kind of concepts, once again, are done in computer simulations, also Mars circulation models, GCMs of Mars now been created, where we then can change what will happen in the temperature distribution of Mars. And then, of course, they provide several layers of protection. You then improve the possibility of retaining the atmosphere you're generating. The atmosphere then produces an opportunity, along with the magnetic field, for radiation protection. There's then several of these processes that kick in. Now, technology-wise, we're not able to generate these currents at this time. They will require significant power supplies. They're primarily going to be nuclear, supplemented perhaps by solar space power, as we talked earlier, but those would be huge arrays. But those arrays might actually be developed and used also in the Mars environment to support power for humans living and working on the planet. Once again, this research is just starting. We need to do much more in this area, and we have the opportunity in the Artemis program to be able to move out in this direction. Thank you very much.
Thank you. I would just note that this process, if we could do it, will be a very long-term solution. We have an ongoing alliance of 14 space organizations undertaking what's called living-in-space.org. There's a website showing things that we've been doing. But part of that process is a special issue of the Frontiers in Space Technology, where there's another article that shows how you could do this much lower power for space colonies, if you will. And this would be an interim step that could be used both for Moon and Mars. But we now need to go on to our next speaker. And Tommaso, I know you have a lot of thoughts and ideas on radiation protection and also on standards and what can be done. So, Tommaso, can you share your thoughts?
Can you hear me?
Yes.
Now I have to find a way of sharing my screen. What is my presentation? I have no idea.
We're running a little bit late, so I hope you can go through this fairly quickly.
Okay. There is some sort of echo. This is not me.
Good.
There is something I don't understand because I see twice I need to leave one of the two. Stop sharing.
Maybe you could just talk to us if you can't get the slides up.
Yeah, I would like also to switch off the other connection that apparently I have. But I don't know where is this.
Well, I think you're on twice.
Okay, let's talk just a little bit about the topic. So my brief speech is about the Space Safety Institute, and the idea behind it is very simple. You may have followed, but this is incredible. I cannot continue like this. There is an echo, which is terrible.
Now we don't hear any echo now.
But you cannot hear me, no?
Yes.
I can hear you.
Can hear you perfectly.
Yeah, I have on my side an echo. I don't.
I have just pinned your imaging to the screen. Also, if you are talking with the other instance of your. Okay, never mind. Go ahead.
Okay, let's talk about the Space Safety Institute. You may have followed a few days ago the news about the funding of the Inspector General of NASA about the Starliner project, the Boeing contribution to the Crew Commercial Program. Here we have one experienced organization, Boeing, which has failed to deliver the right, let's say, transportation capsule to the space station, while a newcomer, SpaceX, has been very successful. What happened? You know that the way the program was organized, NASA decided to take a step back into the development of commercial crew capsule, and basically asked the contractor to be involved to provide, to get insight about what they were doing. Now, SpaceX took this inside requirement of the service contract for the development of the crew commercial transportation to the space station as an opportunity. So basically, they relied on NASA for, let's say, advice, support, and also for some specific small research tasks related to problems that they were encountering. This was SpaceX. Instead, basically, Boeing took an approach in which they said, we know everything, what to do. You don't need to monitor us. We don't truly need much of your advice and support. The end result is that Boeing has failed, SpaceX has succeeded. And Boeing is not just the name of a company, it's a tradition in space, from the Saturn V first stage to being the prime contractor for the US segment of the International Space Station, and for the integration of the entire space station, the development of 300 spacecraft, the development of the core stage of SLS, and so on. So why a large organization with a lot of experience failed, where a much, let's say, less experienced organization succeeded? The point is double: culture, education. I mean, when we talk about a company in this specific field of space exploration, etc., we have to think about the competences of the people. So one team, one project, which is not completely well staffed, make the difference. Apart from the name, it is the size and the competence and the skills that are there that make the difference. This is one aspect. The other aspect is that in the case of space, you don't have prescriptive requirements, safety requirement in particular, because you are tasked to develop the system that, generally speaking, never existed before, or at least not for the kind of technologies that you are requested to implement. Therefore, the requirements which are given by the customer are performance requirements. Performance requirement means I tell you what is the quality of the air inside the habitat of this vehicle, and then it is up to you to find the means to bring that quality within the threshold. This means that you need quite, let's say, an effort to develop from a safety goal a design solution, and that these skills are necessary both on the side of the developer, but also on the side of the organization that has to certify the outcome, the design. This means that the traditional organization like FAA, regulators, which basically based their, let's say, processes on well-defined and specific requirements, does not apply in this case. You need skills and capabilities which are common, for example, to be found at NASA, are not available at an FAA type of regulator. So what is the idea? The idea, frankly speaking, is not new. because has been applied in the field of nuclear power generation, in the field of oil and gas, and consists basically in creating a safety institute, which is intermediate between, the industry and the regulators, what we can call a regulated self entity. So something that is independent, but in any case subjected to government oversight. We need this kind of infrastructure now that we are embarking in commercial exploitation of LEO orbit, the creation of commercial space station basically does not allow NASA to levy safety requirement and safety processes like safety review through the traditional procurement spec, because while an astronaut from NASA will be on board of a commercial space station, there will be also private, there will be instruments developed for NASA and instruments developed for private entities, etc. So you need an integrator from the point of view of safety certification, which by definition cannot be NASA, because NASA has not this kind of mandate. And therefore, the Space Safety Institute would be a network which, by using resources like NASA, but also academy, industry, non-government organization like IAAS, could be providing certification services on call, because you don't do certification of a new spacecraft every day, and also a certain amount of applied research, which is very much needed in support of such development. Where to find the resources? I mean, there are examples in various fields about this. And let's say that the charges that a service organization in the field of certification levy on big projects could be something in the order of 1%, 2%. So if we recognize that the certification is a service, and this service must be paid by those who receive it, then you see that we can get the funds to set up a system which is able to serve a multitude of customers in an integrated fashion under the oversight of a governmental, let's say, organization like FAA and so on. So this is a nutshell what is our proposal. And I would like to finish with a small example that is almost, as old as the United States. Today, you celebrate the 250th anniversary of the United States of America. Congratulations. Almost in the same period, the first classification society, so-called, the equivalent of our proposal of Space Safety Institute, was established by the Lloyd Insurance Register in London, basically providing insurance for cargo based on the condition of the ship. So this is what we are proposing, and hoping that this proposal can be, taken seriously as a way of supporting research in the commercial era, space era. Thank you.
Thank you very much, Tommaso. I do think probably the insurance industry would be a very key part of how this all process works. But now let's go to Adriano, who has also, I know, some very specific ideas and thoughts about what could be done. But I do think that we do remember that it's not only just the technology and the protective systems, but also a certification process and standards that are key to making this safe for radiation, and also maybe safety for habitats, and giving us artificial or simulated gravity. So Adriano, the stage is yours.
Thank you, Joe. Yes, I have, of course, something to add. Sorry, let me try to. Yeah, okay, I'm here. Yes, I think, of course, I'm not an expert of this fundamental discipline. I'm sorry, I'm trying to readjust the. Okay, readjusting, and I also see the timer here. Okay. However, so I'm not an expert. Let me say I am a requirements generator, because in Space Foundation we try to have a discussion about what it is needed, and some of us are also able to make some engineering concept together. So we try to develop some ideas, some feasibility, something like that. And we, of course, we call experts to help us in this in this work. So I put it very, very, very simply, if I can. We have three different environments, let me say. One is the current situation. And let me say, we are still in the paradigm of space exploration. We are trying to move ahead from that, but we're still in this paradigm. And we know that for exploration purposes, the requirements of safety are not so strict. Unfortunately, the life of the astronauts is not considered so important to invest huge money to protect it. So this is one thing. Then we have, let me say, at SRI, we have our ideas of where we should be in few years. So how we should start moving, which steps we should start doing in order to arrive in 2030, maybe, to have made meaningful steps toward civilian space development, because this is our idea, civilian space development. That means people living and working in space. Of course, it's a different paradigm. The requirements for safety, life, and health protection are very much more strict, mandatory, and higher than what we have seen so far. This seems to be too far conception, one another. Our idea of space, civilian space development, and the reality that is space exploration trying to move a little bit ahead. But in the middle, we have some interesting situation. One is the moon programs from Artemis and from the ILRS, the Chinese coalition. And one is the envisioned Mars missions, exploration missions. Why these two things are important and very interesting for us? Because the problems that should be faced, both living on the moon, even for short periods, because don't we hope that the moon base will be something more than an ISS and bring it on the moon? It will be basically the same thing. So they will make shifts of 6 months or so, I don't know. However, they will not face the problem of living residently there for a long time. They will not face problem of bringing civilians to live there. They will not face all of these problems that for us are essential for civilian space development. But some of these problems they need to, however, face. Go to Mars, it requires a long travel. The problem of radiation will be higher than what we have experimented on the ISS for a long time, and the previous stations, of course. And also the problem of gravity is important, because if the travel durates, I don't know, 1 year, 1.5 years, it will be too much long time to remain in zero gravity. So some kind of simulated gravity will be needed for the Mars mission. And we know that, for instance, already an hypothesis was conceived to make 2 starships connected and making them rotating in order to generate centrifugal gravity in some way. So what are we trying to do when we say give 10,000 more funding for this? We are trying to stimulate someone, as Tommaso was saying before, that some governments, some decision maker, to put some more money in that research, to move a little bit out of the boxes inside the Artemis program and boxes inside the Mars missions, because this is the reality. As Bernard was saying at the beginning, correcting me that no, you see, they are investing very much more. Okay, it could be, of course, the data that I have collected, it could be wrong for defect. However, the point is that this research now are only a subset in the budget of Artemis and in the budget of possible studies for a Mars mission. We need more. We need, as Isaac Arthur has made a wonderful speech in our opening session, the 30th of June, saying that life protection in space needs very much more investments. So this is very encouraging, said by the president of the National Space Society. I hope very much that we can join our efforts in this cultural struggle to get more money for Alessandro, for Tommaso, for the researchers, for protecting the life and the health in space. The presentation by James Green was very interesting as well, because he was talking about artificial magnetic shield to protect a planet. I am thinking that if this concept is feasible, it should be feasible also to protect smaller things, like a spacecraft or a space station. So maybe it will require still tens of years, if not more, to think about protecting a planet, especially for the big amount of electrical energy power needed to generate such a big artificial magnetic field. But maybe it could be not so difficult to realize to protect a spacecraft or a station or a space station. Why? Because we are thinking about civilian residents, civilian travelers, people that will have to stay there, live there in a normal situation, living their life there. So they cannot be wearing protective suits or or making every day 3 hours of exercise against the reduced gravity, you know. So we have to think about it in that paradigm, and start moving now, start designing now in that direction is essential.
Adriano, I just would like to emphasize that in the special issue of the Frontiers of Space Technology, there is an article by Jim Green and myself about what we could do in terms of terraforming. But there was also another article that was done on how to do this for a space colony on Mars, so that you have a magnetic protection system to there. And you could apply the same principles and concepts in that article to the ways that you were discussing. But I do think we have to give people in the audience a chance to ask a couple of questions if that's possible. But I do want to thank all the speakers for their provocative ideas. That we do need passive protection systems. We need active protective systems. We need a regulatory system to do that. And we also need to be akin or actively looking at what the private space industry can do and what space insurance standards and provisions can help to do, in addition to a space regulatory safety organization. So do we have time for a couple of questions from our audience? Is there any questions?
Yeah, I would like to make a comment about the study of active protection. Roberto Battistol of the INF and also former president of the Italian Space Agency has made quite interesting studies about the subject, and as part of the research program of the European Union, and we have recognized at our association this contribution by giving him an award in 2013. Now the conclusion from his work, as far as I remember, is that of course can be done, but the feasibility in terms of transportation of tens of tons of hardware to achieve this active protection, magnetic protection, was of course the big problem. So the activities in this field are not completely, unearthed. They have been already studied by several authors.
Okay, I would just like to conclude with a statement that there is a book that's being produced basically with SRI and ACES Worldwide, known as The Future of Living in Space. And in that, there is an article by Jim Green on basically magnetic shielding systems and how they might be established with regard to Mars. There's also a chapter on space safety, in which some of these issues related to what the needs are for trying to go to Mars and settle Mars and what have you, in terms of how we have to do things differently. And that includes issues that relate to radiation protection, and also with regard to simulated gravity systems. So I hope you will look for that book that we hope to be coming out at the end of the year or early next year. And I want to thank all of the excellent presentations by our panelists, but I think we have to turn it back to you, Adriano, to tell us what next.
Thank you very much, Joe. Thanks to everybody here. for participating to this very, very interesting panel. And I think we have to continue the work with Space Renaissance academic committees on this subject, and together with the Living in Space initiative that Joe recalled before. And yeah, let's go ahead. We can now, I think, pass to the last session. That is a Space Renaissance for All Gallery and Culture Beyond Earth. The chair is Bernard Foing, and Robert Katz will help as a moderator. Bernard and Robert, are you online?
Bernard, go ahead.
Good.
Yes, I'm here. Thank you so much. Go ahead, Bernard.
Yes. So, yes, we have a series of talks in the area of Space Renaissance for All Gallery. That is a project that goes in the sense of the cultural utilization of space. It's also an area which we think is very fundamental to Space Renaissance, as we go to space also with our culture, with art, and we use as well art as a messenger to share with society what are the benefits of going to space. Yes, so we have a series of talks that are planned. So let me get the first one.
Yes, Cheryl. Cheryl will be kicking
Yeah,
off.
Cheryl is our first speaker. You have the bio for Cheryl, Rob, or?
I'm sorry, do I have to what for
I have
Cheryl?
a bit. Yeah, so Cheryl is a multifaceted artist and musician, and that made significant and unique contribution to the field of ambient electronic music and visual art since after a long career in health science, and her work is characterized by spiritual depths and transcendental qualities. and she has earned the respect and recognition within the art and music community. She's also a strong advocate in the aerospace community for human cultural evolution through articles, videos, and also various support of organizations. So she's a key partner of and members of our Space Renaissance community. Thank you. So Cheryl?
Thank you very much. Thank you for those kind words and the lovely introduction. I presume I'm sharing my screen again. Is that correct, Adriano?
Yes, please.
I'm sharing it. Okay. And yesterday, did it come through okay? Yesterday, the way I did it worked out fine?
No.
Okay. All right. Well, we'll move right along then. And you can see it, a black screen right now.
Yes, we can.
Okay,
Yep.
perfect. Here we go. Hello, everyone. Thank you for being here. I'm Cheryl Gallagher. Let's get started. This presentation explores current trends in space art, emerging technologies, and how we can use AI responsibly while preserving the human creativity and authenticity that remains at the heart of creative expression. This topic remains controversial. People have strong opinions on the matter. I encourage you to listen to the entire presentation and see if there's common ground in the YouTube webinar below in preparation for this Congress. I go into specifics about various platforms and expand upon some of these concepts. If you're interested, feel free to go watch that.
Any sufficiently advanced technology is indistinguishable from magic. Arthur C. Clarke.
Space art has always been much more than illustration. At its best, it serves three important functions. It inspires exploration, it communicates complex scientific ideas to broader audiences, and it allows us to visualize futures that do not yet exist. In many cases, these artistic visions helped shape public interest, scientific discussion, and even influence policy decisions. As we have embraced evolving technologies and creativity, the results are even more inspiring and complex. Space art occupies a unique position between science and imagination. It transforms data into possibility and helps society envision where exploration might take us next. In many ways, imagination is often the first step in discovery. When discussions about AI become controversial, I find it useful to look at history. Every major technological shift in art has generated uncertainty and fear of obliteration of authenticity. The pattern is remarkably consistent. New technologies often begin with skepticism, then comes experimentation, and eventually adoption follows. Over time, the technology becomes integrated into everyday creative practice and enhances, not diminishes, traditional methods and authentic expression. This does not mean that every innovation is equally beneficial, nor does it mean artists should embrace technology uncritically or compromise standards. But history suggests creative fields tend to adapt, evolve, and ultimately incorporate new tools in ways that expand rather than eliminate artistic possibilities. AI may represent the newest chapter in that continuing story. So what exactly does AI contribute? One of its greatest strengths is speed. Tasks that may have required days or weeks of visual iteration can now be explored in hours. This acceleration allows creators to examine multiple possibilities before selecting a final direction. AI could also increase accessibility. Individuals without extensive technical training can experiment with visual concepts that previously required specialized software tools. For space artists, this means greater freedom to explore ideas. View it as a creative accelerator, a tool that helps expand the range of possibilities available during the early stages of ideation and development. Alongside these opportunities come important questions. As AI systems become increasingly capable, traditional ideas about authorship and originality become more nuanced and complicated. Questions about ownership and intellectual property continue to evolve globally as legal systems attempt to address technologies advancing faster than regulation. Beyond legal concerns, there are philosophical questions. What originality means when machines can generate images based on patterns learned from enormous data sets. How much human contribution is necessary before a work becomes genuinely creative? These discussions extend far beyond space art. They are reshaping creative practice across nearly every artistic discipline. And while definitive answers remain elusive, engaging with these questions is becoming an essential part of responsible AI use. Despite rapid capabilities of AI, human creativity remains fundamentally different. Humans contribute intention. We contribute experience. We contribute emotion, culture, memory, personal perspective, and individual style. AI contributes something else. It excels at recognizing patterns, synthesizing information, generating alternatives, and operating at scale. These capabilities are valuable, but they're not the same as meaning. An AI system that can generate thousands of images of a Martian city cannot determine why that city matters. It cannot decide what story should be told. Those decisions all come from people. Perhaps the most important distinction is this: AI can contribute content, but humans generate meaning. The strongest future for space art is not human creativity versus machine capability. It is the thoughtful collaboration between the two. Current research presents a nuanced picture. On the positive side, AI can support creative ideation, increase productivity, and lower barriers to participation. For educators, researchers, and artists, these benefits can be substantial. AI can generate early concepts, explore alternatives, and facilitate experimentation. However, researchers have also identified potential concerns. One concern is cognitive offloading, the tendency to rely on technology for tasks that would otherwise require deeper engagement. Another concern is reduced critical evaluation when users accept generated outputs without sufficient reflection or analysis. There is also the possibility of over-reliance, where creative decision-making gradually shifts from the artist to the system. What's particularly interesting is that the research does not point to either a technological utopia or a creative catastrophe. Instead, the evidence suggests that outcomes depend largely on how the technology is used. The tool itself is not the determining factor. Human choices are. So what does responsible AI use look like in space art? Several principles are emerging as best practices. Maintain human creative direction. AI should support artistic goals rather than determine them. Use AI as an assistant rather than as a substitute for creative thinking. Practice transparency when AI plays a significant role in the creative process. Respect intellectual property and remain aware of evolving legal and ethical considerations. Document creative decisions. Understanding how a work was developed can provide valuable context and strengthen artistic integrity. Continue developing traditional artistic skills. Technology changes rapidly, but fundamental creative abilities remain valuable across a generation of tools. The goal is simply not to just create images more efficiently. The goal is to create meaningful work that benefits from technology while remaining guided by human insight and intention. For just a moment, I'm stepping into a more abstract and expansive expression about the quantum essence of human creativity and the flow state of consciousness. Artificial intelligence is a valuable tool. Every iota of creative effort is brought into being in the unimaginable vastness of universal space-time, each creative event contributing to the whole. Artists will increasingly become curators of possibilities and directors of creative systems, storytellers who continue to connect scientific advancement with human experience, and visionaries who help society imagine futures that have not yet been realized. The need for imagination will not diminish. If anything, it will become even more important. Therefore, on this level of experience, application is key. I'd like to conclude by returning to the essential idea of this presentation. The future is not human or AI. The future is human and AI. Technology alone does not provide purpose. As humanity expands beyond Earth, explores new worlds, our greatest resource remains the same resource that has driven exploration throughout history: our ability to imagine what does not yet exist. Thank you for your attention.
That was a very inspiring and poetic, I think, which is also a dimension we have to include in our humanity. Is there any short question for Cheryl?
Great job. That's wonderful.
Thank you.
So,
I appreciate everybody being here. Perfect.
Oh,
And
okay,
right
so-
on time. Yay!
Yeah, okay, good.
2 days in a row. Thank you very much. I really appreciate everybody watching, and I'm happy to, if not now, the resources exist to get in touch. So thank you.
Yeah. So, Cheryl, a question. So, do you see some art and culture project that we could pursue together with Space Renaissance in the near future?
Yes, I do. Yes. Adriano and I have had a little bit of conversation, and we'll continue, and we'll figure out how to get it all to work together. I'd be so happy to do that.
Okay. As you see, there is still quite a large interest in this dimension with our audience online and the one that will continue. So thanks, Cheryl. And do we have my good friend Guy Pignolet online?
He
Guy?
was just here. He was here just a moment.
Guy. So Guy Pignolet, yes. I see some vegetation from La Réunion Island. Guy, Yeah, so let's actually I've Guy Pignolet. Yes, you are the next speaker. Guy, tu es le prochain conférencier. Yeah, we move to French now because you know we are very international, and this is one of the official UN languages. Guy, Guy, tu nous entends? Guy Pignolet? Yes. Can you appear on screen? You are the next speaker. Yeah. So in the meantime, I can give some introduction because I've met Guy Pignolet, I think, a few decades ago. And Guy has a long career. He started, he was a student of the most prestigious polytechnic school in France. And he was working at the CNES, the French National Space Center. But also, he has been very active in the education committee of the International Astronautical Federation. Together with Vladimir Sirumianikov, you know, the father of this attachment standard that was used for the Apollo-Soyuz. He coached also students that built some high school satellite, and he developed also a number of initiatives, such as the Réunion Island Space Initiative. I had the pleasure also to visit him in La Réunion Island, where we were inaugurating a monument that was a tribute actually to Vladimir Sirumianikov, together with his Vladimir's son and daughter. And this is a piece of art inspired by space, a gateway between the different world and to space that is still now erected in La Réunion Island and in the Apollo-Soyuz spirit. So now Guy is going to talk about some recipes, cooking up cakes for a peaceful development of a space habitat. Guy, the floor is yours.
Thank you. Okay. So since this is one of the last conferences, I'm going to talk about two very important things, money and sex.
Sorry, can you move your camera in order to take your face, because we only see.
Well, I prefer that you see the green of my garden.
Okay.
Okay. Okay. So then.
That's why I turned the camera and I'm on the side.
Okay. So that's voluntary. Okay, we see your hand. So it's really you, and we recognize your voice.
You see my hand, and you see the plants that grow in my garden. I have a piece of forest in Saturn, in the middle of the urban district. That's it. Adriano, could you put the slides which I have given to you?
Let me check. I don't know if I have it, but if I have, sure. Yes.
I'll send them to you. And well, I can show them like this.
Okay.
This is the Apas cake, the title. Okay, it looks like a cake, and it looks like a docking system of Apollo-Soyuz. Bon. Okay, next one.
Just a moment, I will share it. Okay, share. Share.
Well, it doesn't matter. I can show.
Yeah, but yeah, we have it. But you see, he is a space person. He has always a backup. No, Guy. He has also a manual.
Yes.
But we see your presentation online now. Yeah?
Okay, because well, I'll show the my slides myself, Adriano, because
but, yeah, we have them also. We see the first page.
Yeah, I'm sharing. Can you see it?
Yeah.
Yes, but I'm losing my green gardening.
Ah. Oh, but we see both. We see both. We see the cake and we see your garden.
Yes, but just don't show the slides. I'll show the papers so
Okay.
people can recognize it.
Okay.
Okay. Oh, one of the important things we did a few half a century ago was a picture of our blue planet. And I would say we are changing civilization. Most of our civilization is based on money, making bucks, making money. But this is the end of it, because the system, what I learned in my PhD studies, is that the nation-state system is just disappearing. It's gone. And it's local communities all over the earth. This is technology. Now, for about money, money is dead. For 25th century, money has been the tool of the economy. The economy is where, no. Okay. The economy is where you take resources, you transport them, you transport them, you use them, now you recycle them back to primary resources. Bon. There is no talk about money in this. So the importance of money, which was invented 25 centuries ago, is that you can count with money, you can make operation at the time that the Greeks were developing mathematics, and Croesus, king of Turkey, invented money in 6040 before Jules Caesar. That's it. Well, this is over. At the same time as the Apollo, there was Woodstock, which was the beginning of another generation. Okay, get it. Okay, Adriano.
Yes.
Can you take off? Can you take off the slides? Your slides.
Okay. I stop sharing. Correct?
Okay. Yes, please.
Okay.
So Woodstock was very important. That was at the same time as the Apollo things. Well, our world is run, I said, by the economy and industry, and this is over. This is finished because as Ruth Tumlinson said in a SRI conference, the politicians and the heads of the big companies are in their heads 1 century late about the current development. And now, over the past generation, there has been the development of computing and digital and artificial intelligence. And finance people still use that to make accounting, which is an obsolete tool. To make the economy with finance and accounting is like trying to make fire by brushing 2 pieces of wood. This is totally obsolete. But most of our leaders, okay, so-called leaders, don't know that. So there is another part of life which is important. which was invented by the Greek about at the same time, which is cooking and dessert. And this is a spoon, which is an economic tool, very important. That's what I am going to talk about. Bon, there is a connection with sport, bicycle. And about a century ago, there was an industry person who was sponsoring the Paris-Brest bicycle race, and he asked one of his cook friends to make cakes which are known as the Paris-Brest. Okay? And well, this is what the typical Paris-Brest will look. Okay, you see, you have to work with your imagination. It looks like a wheel of a bicycle. Bon. In 1975, our friend Vladimir Sirometnikov, you know, he graduated from Bowman Institute in '56, and he was living in the north of Moscow. One of his neighbors told him, "Come with me tomorrow." So they went to a factory 1 hour by train north of Moscow. And he was introduced to a big tall man who said, "Congratulations, young man. My name is Sergei Korolev. I am doing the first artificial satellite. Do you want to be part of my team?" And this was the first job of Vladimir Sirometnikov. So every day, Vladimir went from the house of his parents near Riga station in Moscow to Padlipki, which became Korolev today, and 1 hour of train in the morning, 1 hour of train in the evening. And what he did, he was reading My Tailor is Rich, learning English. So he was one of the few people with energy who could master English. And he worked on a docking system with Energia. And the docking system, you know, when you have a spacecraft that go fast, okay, you have a probe. Okay, you have a probe that goes into a cone, and when it adjusts in the bottom, but this looks very male-female kind of thing. Okay, and when Vladimir was in London in the early 70s, he met some Americans who do not like war. You have some, and they had one Saturn rocket left. He said, "Let's use it to have a handshake at the middle of the Cold War in the middle in space." But of course, they could not use the classical docking system because who would have the male part, who would have the female part, the Soviet or the Americans? Politically impossible, technically simple. So Vladimir invented a docking system with 2 rings that would match, and you would have petals, 3 petals on each side, 3 petals on each side that would match and adjust, and it would be the same. So he got the Lenin Prize for that. 20 years later, he had the Cold War was over. Russia had taken over from Soviet Union, and Vladimir went to Rockwell in California for 1 year to build the APAS docking system on the American shuttle. And one of his students was someone who became my friend 2 years ago, space woman Elaine Collins. And we met because, for those who don't know, this is, okay, I'll show you, the biggest part of myself, and I have a small part which is at this time 145 million kilometers from planet Earth on Celestis station Enterprise. So I am the French person who has parts the furthest in the whole solar system. That's it. Bon, so eventually they did it. And Elaine Collins was the first American woman to command the space shuttle, and she was selected to do a test docking between the American shuttle and the Mir Russian space station. So I was with Celestis at a conference in Cape Canaveral, and we had lunch, and happened to be, and it took a few words when I was going at the buffet, and I met with Elaine Collins to find that she was the most famous American spacewoman, and I had been in the 90s, as Bernard said, the chairman of the World Space Education Committee. So it took a few words to find out that we both knew Vladimir Sirometnikov, and I say, we have a science fair in Reunion, would you come and give a special speech? She said yes. So in November 2 years ago, Elaine Collins was in Reunion, and for her birthday, we gave her a cake which was the shape of the APAS system, and this was the cake we made looking like the APAS system. Okay, now a few years, a few months later, I went to Cape Canaveral to see my hair going to the Celestis, to the Enterprise Celestis station. And okay. And Fred Hayes was to give the speech, but he had a cold a few days before, and he was replaced at the last minute by Elaine Collins. So after a few words, we found that we both knew Vladimir Sirometnikov, and we say, we have a science fair in Reunion Island in November, would you come? And she said yes. So it was her birthday by the time that she came to La Réunion, so we make a birthday cake. That was a big one, and that was a small one also. And the importance is to have a center and to have the 4 petals. And okay, so cooking is very important in all the world, and people in all the world can make cakes or pizza or omelettes or whatever, it doesn't matter, that will have the shape and put some decoration to make the APAS cake. So if Space Research Initiative Space wants to share this idea of making cakes worldwide, this is another approach that is not intellectual, but that is intellectual, you know, is gone. Mankind, the hydrogen came 13 billion years ago. The mankind came a few 100,000 years ago, and modern mankind began 10,000 years ago with cooking. And cooking is today something very important in the life of all people. And they don't have to be intellectual. Because intellectual, what came 5,000 years ago is writing, especially with the books of the religions, but transcendental things, you cannot talk about it. You cannot talk because, not because it is forbidden or anything, but because language cannot carry transcendental ideas. That's it. Thank you.
Thank you very much. Merci, merci Guy. So in summary, so what are the main ingredients for life? You know, Big Bang, that gave us all the ingredients, hydrogen, what we are made of, our humanity, space, but food, cooking, and also doing that all together. So let's look at the opportunity also to see you again, even last some time we meet in Paris at the opportunity of the IEF committee meeting last week of March. All of you are invited to join in. We can get you to join us there. Any question for Guy or comments? Great stories about APAS, about Cerium Natnikov. So that has this ring that connected Soviet, Russia, and Western world, and that we have even reused towards space station.
Vladimir Volodya Siromyatnikov was in 75 when he had the Russians, and there is Apple TV who made a remake of Apollo Soyuz, where in the 90s a woman who is the head of NASA decided to do the Apollo Soyuz in the 90s.
Yeah.
And but a war is just going, you know, like the kind of stupid wars that we have plenty, to explode. And the President of the United States is in his presidential plane. And there is the commander of NASA, the woman, says, we cancel the whole thing, the Apollo capsule, you come back on Earth. And they have been for a few days in front of the Soyuz, and the commander of the Apollo said, no, here I am the commander, I'm going to dock. And if you want things to happen beautifully, you better give Houston the order to help us. And then the woman said, I'm speaking here for the President of the United States. I give you the order to come back. And the commander of the Apollo start making the thing. Then the head of NASA takes a breath, and here at Houston, I am the representative of the President of the United States. I give the order, help them to do the docking system. And in the presidential plane, when there is a handshake, somebody tells the president, look at the TV, and he looks at the TV, and he sees that, And he says, stop the preparation for war. That's it. That's Apple TV.
Beautiful. Make space.
Make
Make peace, make space, not war. Yes.
Yes.
Thank you so much, Guy. So many stories to tell, to write, and we could also spread them through our Space Renaissance community. But we have to move on now, and I think I'm the next speaker, so I will try to fit in the 10 minutes that are allocated to me, and I'm going to talk about our project Space Renaissance for All Gallery. But I wanted to put it in a bit larger perspective of some initiatives that we have started already some 20 years ago. Oh, okay. I share this. You see my presentation?
Not yet. It's coming.
You see it? First slide?
Yeah, not yet. It says it's starting. Oh, there we go. It's all set.
Oh, okay.
It looks good.
Yes. So I want to pay tribute to really a cast of a number of collaborators that in the last 15 years have been working with me on some initiatives that are linking space, culture, and art. I put them in reverse the chronological order. So the most recent are some of you that were involved in our Space Renaissance for All gallery. We have also some initiatives in the frame of the IAF, Itacus Committee on Cultural Utilization of Space. We have also did some work with our colleague from the Yeoman Mars Analog Astronaut Training Center. We had also some activities we performed with Willem de Koning Applied Art Academy in Rotterdam, with also the Fine Art and Conservatory Academy in The Hague, where we have conducted some art and space curriculum, where we had students inspired by space. We even had some work with the late Jim Burke on defining content for a Moon Alexandria library. And before that, we had a series of festivals called 2 Days Art, where every year we were organizing festival bridging art, and we organized some space event. And we worked also with some artists for a curriculum for art science. Before that, we also had some field campaign of our astronaut training where we invited some artists. And since 20 years also on the musical front, we have had a quartet. It's called Aztec Space Strings. So it's some space experts that play music together. Okay, next slide I try to have. Yeah, so let's see some 15 years ago, when I was working at Aztec, the Open Space Research Technology Center, we organized even a Moon Life Academy workshop where we had a mixture of scientists, engineers, artists, designers, all disciplines, and we had a full week workshop designing a moon base, but also what art activities we could perform there. We brought the artists on the surface of the moon together with our lander that we had built, and we organized also activity in the city, in Amsterdam, and of space and art in the street. And here also we brought some of our artists close to the space station module that we have exposed at Aztec. So here you see some of the artists on Mars together with the lander that we have designed in the frame of Google Lunar X Prize. After this, we started a curriculum together with the Fine Arts Royal School in The Hague and Conservatory, where every year we had some 60 students for 3 months that were developing a curriculum about art and space. And this led for them to develop individual artwork, but also performance and exhibitions that were then shown in various international art places. So in the frame of this, we also invited artists in Aztec, so also some musical artists, you can see, performing music in a surrounding of a space in front of the Columbus module or in front of our Moon and Mars rovers. We have also a module where I can log the artist inside the Columbus module, and then they can imagine that they would be playing in space. We organize also, we are invited to join the 2 Days Art Festival. It was a series of a yearly electronic art festival, and we organize in the city some events also about astronomy and space, also mixing space lectures, workshop, but as well performances. We even brought our lander in the middle of the city. We landed just in front of the town hall on the main square together with some of our astronauts. These are 2 Polish astronauts with whom we work also for analog campaign. Eventually, we also performed with our Aztec space strings. So here we had some jazz group. We had also classical professional pianist, Maria Prokofieva. We had our jazz band, and we played also in the central place of The Hague some music that was inspired by the moon and by space. Another set of events, you know, we have a large concert hall in Amsterdam called Concert Gebouw, and we participated to a general Star Wars concert. And just outside the concert hall, we brought our telescope, we brought our astronaut, and various people celebrating what is going to space. Not for war, but for peaceful citizen development. Another set of projects was developed in the frame of the Global Science Opera. This is an initiative that started first. Before us, there was a Global Science Opera on the theme of particle physics together with CERN. And 1 year, we had a theme about Moon Village. And this was 20 classes all over the world of different countries performing an opera where each of the class would play one scene of the opera in different styles. Some of them were dancing, some of them were doing poetry, some doing robotics, and then this was broadcast on television all over the world. And this has followed also on other themes after that, linked with water on Earth. The theme for next year would be peace. And then we plan to also contribute to show what space can bring to peace. And for the Moon Village, the story was about Sophia, a girl born on the moon. And this was following some of the story I wrote about Moon Village, that in 20 years, I will be living on the moon, but also there will be the first kid born on the moon. And the story was, what are we going to teach them at school? And eventually, some of them will want to come to the Earth. And as Adriano is afraid, if they have lived all their life on the moon, how can they adapt to Earth's gravity? So there was a big technical challenge. And in the story, thanks to a little robot, and we managed to get Sophia to Earth. So we also have worked with IAF, International Astronomical Federation, in particular its committee, ITACUS, on cultural utilization of space. This was created some 20 years ago to provide a liaison to various cultural organizations and bring them space, and to promote and facilitate the innovative utilization of space for benefit cultural to cultural sectors of society, with art, humanities, entertainment, popular culture. And some of the activities is to help in the production, preservation, representation, education of cultural aspect of space, and advocating as well that space is also for culture. And so we have organized a number of events every every year we meet in March in Paris, last week of March, with a committee, and you can recognize some Space Renaissance members that have been a member also of this committee. And we are also, with Itacus, present to organize a session as an International Astronomical Congress, and we have also some side events, mostly with culture and art. So I served as a chairman of this committee until 3 years ago. And but we have a former Space Renaissance colleague, Marlène Lausier, who is now the chair. Sabine Heinz is the vice chair. And so I would recommend you also to connect with the Itacus committee. We are also Naum Romero, who was the previous chair. Here, for instance, some events that we organized with the committee in the ISC in Bremen. And you see, we have all countries, all generations represented, a few astronauts, anchoragers, our good friend there. Now, I would like to go towards Space Renaissance Gallery, our
Time
latest
is over.
project.
Werner, your time is over.
Yeah. So let me give me 2 minutes on Space Renaissance Gallery. Thank you.
Okay.
Like you did for the others. Yes. So Space Renaissance Gallery, we built on a payload that we have launched to space on the International Space Station. And this payload then was adapted to make a call for artists to send some of their activities in space. So first we had a call called Moon Gallery, and then we have flown a test flight model of this Moon Gallery onto the International Space Station in 2022. It stayed 1 year in space, and you can see it there. And more recently, 2 years ago, we developed a platform called Space Renaissance for All Gallery that include, on one hand, a tribute to 40 partners of Space SDG 18 and Lunex collaborators. So it was paid by Lunex Foundation, not by Space Renaissance, that doesn't have so much budget, but we made this gallery available to promote Space Renaissance. We used some of this tray flown previously to the ISS. We had science samples from various universities. We had art science samples from different groups, Art Moon Mars, Moon Gallery, Moon Mars Museum, Space Renaissance. We have a digital library, and we assembled it in the Netherlands. And that's how it looks like. It contains also samples from Earth, from all continents, also some seeds that come from different areas, and 25 pieces of art, some graphical art, like Sabine Heinz or Daniel Futzeler. We had some sculpture by the wife of an astronaut. We have various art pieces there also for Earth observation and so on. And we had even some meteorites from the moon, Mars, and asteroids that came to us, and we sent them back to space. So we launched that 2 years ago, and actually it was the opportunity that I had to meet Ghanim just before the launch of our capsule doing a living planet. And then we have a copy of this gallery we bring all over the world to promote Space Renaissance for All. So this was in a Global Exploration Conference in India. This was in the Shanghai conference with 1,000 professionals. You can see here with some Nobel Prize, with some young people, and with the Director General of UNESCO. We brought it at COSPAR event. We brought it also at UN. We brought it also in an event called IP Space with the son of President Bush, with some astronauts, the first Chinese astronaut, celebrating Space Renaissance for All Gallery. We brought it also at UN Copios. Here, double picture with the CEO of IP Space. And so that's how we use also this symbolic, but also real payload that went to space to talk about Space Renaissance for All. Thank you very much, and looking forward to future projects.
Terrific.
So, okay, so clearly we plan to launch it again in 2 years, and possibly to International Space Station. And we are looking also to integrate some input from some of you, also from some of our partner organizations. Now let's move to the next talk. And this is given by Dr. Gulin Dede, and she has. And indeed, I met her at the occasion 2 years ago of the launch of our Space Renaissance Gallery, and I invited her to join Space Renaissance, and I'm so happy that this happened. We have also collaborated on a number of projects. Gulin is really an expert in space. She has had a key role in the definition of some Earth observation mission together with ESA, and also she has trained as an analog astronaut with our program. So she joined Space Renaissance and take a key role now in helping her to organize and to develop our activities for the future. But she has also very special interest into future role and artistic aspect of space. So let's give the floor to Dr. Gulin Dede. Thank you.
Thank you very much, Bernard. It's a pleasure to be online on this very interesting cultural perspective of space. So now looking to your slides, I just realized in 2016 we have crossed ways as well in The Hague. So I was there visiting the exhibition, and it was amazing, but I never knew the person who was behind the preparation of all of that. Now that I know, so we have had occasions, but really, truly our meeting happens recently, but strongly. So let me just put my paper on the screen. So I will walk you through my paper. Don't worry, it has some pictures coming up. Because also, just to expand a little bit on my involvement with space art, it started really quite practically because I don't have an art background, as I had been mentioning, as well as yourself. I come from a pure technical background, so I'm an engineer, and I was already working in space with Earth observation missions, Copernicus, Sentinel satellites, and also a bit of space policy, but later analog astronautics. So that is the part where artistic side became more evident to me. And then I started thinking more about how we can convey the message, because the things that we do on the space front remain very technical and it's difficult to understand for the broader community. And therefore, there is a way to ease into that through images, symbols, objects, and memories and stories. So during the analog astronaut mission, I was also the crew commander, and I realized there's a lot that goes into also the emotional part of the things. So the habitat, the crew narrative, and the mission patch, the suite, the photographs that were taken on the spot. So I had an Instax camera with me, and even those became parts of the story. And then I realized there's art everywhere we look. This is why my presentation today, my paper today, talks about From Orbit to Exhibition, developing the Space Renaissance for All art gallery as an art media and outreach platform. So the first time I saw it at your hand, I realized, oh wow, this is just the beginning of something really big. And introduction to Payload as an opportunity, but also as a cultural platform, was really inspirational. So then I looked into a little bit where this has been, investigated before. And even in the very early times, we see this, for instance, piece of art that was dropped on the surface of the moon in memory of the fallen, the art piece itself is called Fallen Astronauts. So it's a memorial, and this is also a way that culture has always been into it, this way or the other. So a number of prominent precedents in space art had been useful for me to investigate in this context as reference points for thinking about how we can further shape the future of the art gallery. And also, this is just to show once again what Bernard was in detail explaining us about. So this is a Space Renaissance for All art gallery payload, which had been to space and back, and that's all the more inspiring to hold it at your hand. And I really appreciate Werner taking this everywhere he goes, carrying the Space Renaissance ambassadorship to the places through art, and it's always a wonderful conversation starter. People gather around it, they try to see it, they try to touch it. Even that moment of experiencing it becomes a story for them that engages them more to space activities. And that is just, as I felt like, the beginning of the story. So there are other examples, of course, cornerstones of space art that are relevant to art gallery as far as I have figured out and put together in this table are different from pre-space flight imagination to art, to NASA's art program, to Moon Museum, to this cosmic dancer example, which had been through Art Wood's sculpture on the mirror, and also astronaut as an artist, astronauts as artists themselves is another perspective, and orbital and lunar galleries and immersive exhibition practice. So after my analog astronaut mission, which was in August, I took the chance to give myself some time and figure out what art is all about. And I went to the Ars Electronica Festival that takes place in September. So it was like a roller coaster, parting ways with Isa, becoming an analog astronaut, going to an art festival, and everything came together. So that was really an eye-opener. If you have not been to Linz, Austria, for the Ars Electronica Festival, I definitely recommend that you go there and visit it for yourself and have that experience really of immersive art with haptic sensors, with one ton of technology that goes into production of this piece of art. You really feel like you're surrounded by it. This could also help us consider habitat designs differently. So here's another example of art in the city, so to say. So this is from NASA's art program, and it appears side by side at the Houston street. And it's also a rather recent installation. So when we go to look into examples, what could be a different curatorial sequence for space art renaissance, the way we would like to, we could think about it in the future. So when I thought of it a little, I came up with this sequence. So the object, the orbit, the story, and the return. So this is reflected also in the nature of the Space Renaissance Gallery as well. But it's a little bit more than that, because on the return and after the return, we can now go towards museums and other exhibition formats that would be more interactive and with other things around it. But of course, this being said, we need to put the mark on the budget. Things come with an associated price tag to it, sadly so also for the art world. And culture is sometimes the least on the row of the things that we got to do, but it would be best if we practice technology alongside with its cultural interpretation and expression through society as well. So it's really received the way it could be most impactful. So I was not able to put here the Ars Electronica Deep Space 8K immersive art science exhibition model, but if the link is available here, it's due to image permissions. So you can go and check it online. If you had been to any ESA event, they are also installing ESA and DLR exhibitions. So maybe that's what you experienced there already. So those are the kind of things we can talk about when we think further how we can express and expand on the impact of this cycle of the object going to the, let's use the moon for this example, going to the moon and back, for instance. So the first missions are always interesting. That's another thing that I found during my research. So the first access and also the new cultural constituencies are very interesting to study in terms of art. For instance, I had the chance to visit Turkey's first manned mission space exhibition. So this had been taken, this had been really utilized well, and there were installations about it, and also the mission memorabilia was presented. So those were very inspirational for a whole nation, I must say. Also, being Turkish myself, I saw that how it moved people, especially young generations, because the museum had a policy, not touching is not allowed. So that was, you really had to go in and experience everything. And they had also so many other things alongside this particular mission memorabilia and concept, but other things that are relevant to space as well. So a lot of experiments that students or young people can try out. So that was very nicely received. And a second suggestion could be presenting the work of indigenous peoples and artists, because indigenous communities have long-standing sky knowledges and visual traditions and relationships with celestial observations, yet they remain underrepresented in formal space.
Time, but
I'm
okay.
hurrying up. I'm
No.
of it.
2 minutes.
Take what you need. Minutes.
2 minutes,
Okay,
and then
thank
we
you
have
for
10
your
minute
generosity.
discussion. Yeah.
So actually, this would be one piece of artwork. So I figured out there had been some examples, Canadian initiated, and this is the Lunar Codex for some indigenous cultures examples that were carried into the art scene through space. And last but not least, the power of meaningful collaborations is what I would recommend for SRI going forward. Mm-hmm. So if our gallery's development could be pursued also through initiatives, for instance, as similar to the one that we see here, it's very much institutionalized. We see the organizations here, UNOSA, DG DEFIS, ESA. So I think part of it was also DLR relevant, but I see ASI here as well. So I think that's all the more interesting to mention. Let's think about this is the view of the city from Bonn, and as you walk through the sidewalk, you are surrounded by this conversation going on with space and the city. So I think those are very nice formats, which Bernard also introduced to us. And I have here a proposed program for what we can do with our art gallery, given the funds availability. We can do further curatorial and institutional value creation around our artwork. So those would be my last words. And I have my references. You can look into my paper online, which will be also available. So I hope you like it.
Yeah, excellent. So that's a bravo. That's a
Bravo, wonderful.
It's really within the spirit of Space Renaissance, also Space Renaissance Gallery, but even goes beyond because we project towards the future. One comment, the Space Renaissance for Gallery is not only art. So we tried from the start, also Moon Gallery, to get people together, artists, scientists, to work together. Also because special condition how to develop payload material to space so the artist can learn, and also the engineer scientists learn from the artist. And also it helps in the budget side, because most of the budget I got from Space Renaissance for Gallery get from my research funds, not from art funds.
Yeah.
Yeah.
True.
So,
also,
yeah.
There was the occasion that I presented my artwork to UNOSA. Bernard, you would remember that when I presented it to you as well. So they loved the idea. They wanted to allocate Rotunda. If you know the Vienna International Center, it's the center of the building. It's the heart of the building. And my exhibition that would be curated together with Ars Electronica would go up there for presentation to public. However, though everything worked well on the approval side, unfortunately, in last minute funds were not available partially, so we had to put that off. Now there is consideration for the Vienna Technical Museum to host that installation for 2027. Given again the availability of funds. So this is also an important area. I appreciate that SRI is looking into it, not just the pure technical part, but also this cultural outreach, which is really important, and you have done it so well, Bernard. Thank you.
And another dimension also, which is important, is the fact that it's a collective project. So in our case, Moon Gallery, we had 100 artifacts. Also in Space Resonance for All Gallery, we had we had 20 slots. We managed to put several artists together in one slot. We packed them, and we had also 20 slots to pay tribute to partners. So that was this dimension. So space, art, science, technology, and partnership. And with this way, I think it has a much stronger message than just art. Because we are all polymath, so we are all artists, we are all scientists, we are all engineers, and so we have to cultivate all these dimensions that we have, and we do that together. But now I think that's the end of the session. But you have 10 minutes. I think Gulin, you are the chair of now the discussion of what could we do next, and maybe we could start with some of the panelists. Cheryl, if you have any comment, and then we will go along those that want to talk and propose action for the near future.
Thank you. I'm happy to do that. Fabulous to hear what you've been doing, Doctor. That was just terrific. I also, yes, I know how much it means too.
Yeah.
I also had some art go to the moon last year with a different initiative, and now I'm running through my head who those partners were that were involved with that, because there were some pretty major commercial type people that had initiatives that were also part of putting the art in space. And so I'm going to get in touch with those people. I'd love to have your contact information, Gulin, Doctor. If that would...
Yes, definitely, Cheryl.
And we could coordinate some of those things, because I actually got to go to Cape Canaveral and watch it go up, and it was really fun, super fun.
Amazing. Thank you very much, Cheryl. I'm so inspired by your video and how you reflected on the AI and human and machine interaction. That captured me both from a technical part as well from the artistic perspective of it. So I appreciate that.
Thank you. It's a really touchy subject, and people are pretty black and white about it. It's like, no, you shouldn't have. And I'm old enough to have grown up with the technological advances and watched that process of integration grow. I know I was showing like cavemen, and I'm not that old, cavemen and things, but every time we've had a technology, the reaction, the knee-jerk reaction is like that. And yes, we can observe that there's misuse of AI currently going on as we figure out those parameters, but not any different than Napster ripping off all the music and when the internet was much younger. Those things, we work through those things, and then eventually there's there's more cultural evolution that comes from that. So thank you for listening to that presentation. That's part of my effort to try to help that process. And actually there's other initiatives going up to the moon, so that would be another thing to think about, is if we can partner with them, and then there's less cost and less investment both directions. So I can see that I can be helpful. I have to join the committee.
Very good. So please join our committee.
Put me on the list.
And art, Itacus. So we have also some payload that are traveling to the moon, and we managed to integrate also the cultural part on this payload with a cost paid. Like I have 2 instruments that are flying to the moon.
Oh, very
One will
good.
fly to Mars, and
Nice.
like we have done, for instance, for Beagle 2, we had some calibration mask with different colors that was repurposed for art. So
Oh, very
also we can
nice.
find some tricks
Really find some ways
yeah.
to incorporate art
Yeah, to
into the
incorporate that.
scientific instruments.
Yeah.
That would be
Yeah.
that sounds fantastic.
And
really.
also because in the future, our society needs people that are good in science, in technology, but also are creative and are listening to art. So
Well,
that's also how we train the next generation for
It's-
space renaissance.
Absolutely,
Yeah.
and it just lives into the theme of the whole Congress here of,
Yeah.
Living in space. We have to live out there. It has to be a life. Those points that Adriano was making are so valid. It can't just be, a bunch of humans in basically the back of a truck, right? Like a container. We really have to live out there, and there has to be outlets for us to continue to develop as a species, I think.
Very good.
So
yeah. So Azizal, you had some comments, and then let's open it for everybody. And I would like that we end with some plan for action. But let's listen to everybody before. Azizal? Yeah.
Yes. Okay. Okay, good. First, I want to say this is great this week. Okay, I'm happy. Okay, but I want to say something. The small pieces that were sent to space, okay, there was one of them from Kuwait, okay, and Ghanim told me that we want to send something from Kuwait. So I was doing some related work in an archaeological site, okay, just doing some observation. And anyway, so I brought 2 pieces, okay, one of them from Ur the Third, goes to Ur the Third, which is 2100 BC, okay, and there we discovered small tablets written in cuneiform, okay, and it goes to 2100 BC in an island, okay, in Kuwait. And the other one, which is the location next to it, in archaeology, they build over on top of each other. A Hellenistic temple, actually, it's the Artemis temple, and this is part of it.
Wow.
See? Okay, if you can see
wow.
it, part of it, okay. So, but this is a shred because in any archaeological dig, they have the main thing that you don't touch, and they have the things that you can. So I took from that, okay, with permission, and these are the ones that you sent. And thank you for that.
Yes, thank you. Thank you for the contribution of Kuwait that you organized together with Ghanim and that's well. And yes, so we had a few contributions from some countries, region. Also, we paid tribute to some countries through seeds that they provided. And so we have like a microcosm we send to space. But we want to follow that with some events and also some action. So as Gulin mentioned, we bring along the spare of the gallery, not the one we send to space, but the one we have here, and we show it around. And we are going to have an opportunity to launch it again. And but this could include also some artifact and also some pictures of Space Renaissance members and partners. We will show it at some upcoming events, like at COSPAR assembly in Florence in August, at Europlanet conference in The Hague, and at IAC. So we could organize also some event at this opportunity, also to define the follow-up actions. And yes, and we are open also to some proposal. We had also discussed some project which is called Art to Mars, defining also some artifact that we could send on future mission to Mars, but other project as well, where we integrate in everything that goes to space, we integrate the dimension of culture and art together with science and technology. Frank wants to comment?
Yes, I was wondering if part of this program would allow for not only sending seeds, but also retrieving them, like the Chinese have done in some of their mission in low Earth orbit, but it has also been done for the Apollo program too. We brought back some trees from the lunar surface. I think that would be terrific for the archaeology crowd to have some plants that were exposed to the background radiation of space and have come back to tell a tale.
Yeah, so there's a great story about that. Actually, in the frame of our moon gallery, we had an event in Padova, a special event in Padova, where also there was some seeds that were given from the Apollo time to Italy, and there were some trees that were grown, in each state of the US, but also other countries. So also a great story about life in space, and yes, seeds are also amazing, inspiring vectors for talking about bringing life to space, and it's cheaper than an astronaut. So, any more comment on culture and art and Space Research Gallery? As I see that with Gulin, we will collect also some of your ideas and input, and we try also to eventually formulate something at the opportunity of IAC as well, and we'll present it and then look forward for next year.
Yes, I want to add just a few words.
Yeah, yes, please, Adriano, yeah.
The topic of reconnecting rationality, science on one side, and intuition and spirituality on the other side, I believe that art is a good connector.
Mm-hmm. Yeah,
is the right connector between, is a very, very direct connector between rationality and intuition. So I would like to encourage, because everybody has an artistic part in our
yeah, and by the way, we also sent music from Adriano to space. So
that's
we,
true.
we
Now that
we had recording of several musicians, and we sent it also with Space Renaissance for all gallery.
Some nice jazz.
Now that maybe I will have a little bit less work to do, I hope so, because we will have a new CEO and many things will change, and maybe I can give some more time to my part of my personality, and produce something more on that side. Okay.
And you're all welcome for the event we organize in The Hague. If you come, we will have an art and a music event, clearly, that I can host. And we have to see if we can make also something small in Antalya at this opportunity, some music. Not as big as what we did in Paris or in Milano, where we brought the whole equipment and all the guitars and instruments, but maybe also with local artists.
It would not be possible for me to bring my guitar. And
but we will have a guitar there. We'll find some local guitar.
Okay, let's see.
Yes.
Okay. Maybe we can close.
That close the art session, but maybe we should also close the overall, let's say, Congress with reminding, all the sessions that we had. What I would like to ask is, there was amazing quality of content, also quantity and length, but I think really it was very well filled. We have the papers, so that's good for the long-term heritage, but also we had this beautiful summary that were written also every day that we already started to post. But also if some of the chairs want to make like a mini summary or from their perspective, what is so important in their session, it will be nice to compare that relatively soon, and then we could distribute that as a like an immediate legacy of the Congress.
Excellent.
Yeah.
And yes, I think this is the first time that we are ending almost in time. That's a great news, too. Okay, before making a general short wrapping of the Congress, I think Mike Helton want to say something?
Yeah, okay, excellent.
Yes, I'm a new member, so I'm not sure, but do we have access to the recordings that were made of the talks?
Yes, everything will remain on YouTube. The 5 days will be there forever. Okay. So we will publish again all the links, and probably we will also make an indexing of each day in the description of the YouTube video. You will find the links to the minutes, exact minutes of each talk. And that will be also reported in the ACTA pages, because, yeah, there is still a big work to be done after the Congress to make the ACTA and to make available online all the pointers to the talks, to the papers, to the presentations, and everything. So everything this will be produced, as well as a book collecting all the papers, all the presented papers. Will be not the PowerPoint presentation, but the papers will be regrouped in a book and published on Amazon. So it will be available. Yeah, that's it.
And one more question or comment. Is there a committee for funding activities here, and so we could maybe join that and provide either some funding and some ideas about getting some funding?
Definitely, funding is our main problem, because if we have more funds, we can travel more, we can go around and giving lecture in presence and presentation in conferences. That is definitely something we want to address with the new.
And we can support also.
Let's say
we can support young professionals in some research project and studies. Like we have this Medici fund that is dedicated for young professionals. Actually, in parallel to that, I'm giving now a grant to 12 master students. They do their research master with me, but because they are also joining Space Renaissance from LUNEX
However,
and ISU.
Mike, if you can and you want to make a donation, you are welcome. To everybody, I will put the link here now in the
website
chat.
is
Also, if you have ideas for funding, that will be very welcome. To make to make events for funds collections and things like that. I don't know, dinners or anything, cultural events targeted to collect funds. That would be interesting ideas. If you have, please share.
We are also open to corporate funding. So if you are, if your company and so on is interested to provide some funding on some condition, on some joint activities, some joint events, we can accept corporate fundings along, project that have the values that we serve. So civilian space development.
Okay. Well, I want to.
Do we do a group picture also for the end?
Proceed. Yes.
Okay.
Why not?
Yeah, let's do another group picture.
Let's go.
So if you can all put your camera or your avatar. Yes.
Yeah.
And then we can take a group picture.
I think there are still more people now. Please come on with your camera.
We want to actually see you. Turn your cameras on.
Yes, let's put the camera on.
Come on, everybody, with your camera.
And put the gallery.
Aldo, Amelie.
Come on, we won't sell it for much.
While we're waiting, I just want to make one comment.
We fly the picture to the Space Renaissance Gallery, to space.
Frank L'Italien. Greg Harrison.
While we're waiting, I just want to make one comment.
Yes.
And that is to be happy Happy 4th of July to everybody.
Oh, yeah, that's right.
And if you're not in America, come on over.
Yeah, 4th of July we celebrate. Also,
I'll take the cup.
Also, important date. Important
I
date.
think
20th of July, International Moon Day. We'll have a special event here.
Natale,
All over.
video camera.
And all of you think 10th of July is
Niklas.
the early bird registration deadline now for ISC.
Bernard, please shut up. I'm trying inviting.
Yeah, no, but yes.
Come online.
While everybody is getting a picture, yes.
We're still
10th of
waiting.
July to register to ISC, early bird.
Marie-Louise, please
Yes.
switch on your camera. Natale,
still waiting
accendi
for
la video
people.
camera. Niklas. Pierre De Vos, Victoria Ustimenko. I saw you there, but you're switched. Okay. Okay, let's take
with all the names.
Let's take a screenshot now.
Yeah.
Okay. Me take Photoshop.
Oh, and everybody wave.
But thanks to Adriano and all the team for a very beautiful program. Huh? So.
However, okay, now that we have made
thank you so much.
This thing, let me say something more. Tomorrow is the last day of our Congress. It will be dedicated to voting the new president, the new board of directors, and the final resolution. There is a draft of the final resolution that we will circulate among the board tonight, and in order we are ready to present it tomorrow. And let me say that this Congress was really great. We had beautiful high-level presentations, papers, and discussions in the panels. So I'm really happy, even if it was, of course, a big work, a big tiring work, but however, it was worth. And now we can say that some important concepts emerged as it happens in all the congresses. We had some important points that will be present. Okay, I can maybe just take I can read if you like. We have more than 12. We have 16 points now, 16 goals in our final resolution, and they are call for an international ban on space weapons, promote the conversion of military industrial capacity towards civilian space development, promote the Space 18 Sustainable Development Goal, empower young generations, increase investment in life and health protection in space, design future space infrastructure according to humanist principles, advance free space habitat concepts inspired by the Gerald O'Neill vision, establish the first permanent and semi-permanent outposts on the moon. Okay, I don't really understand what does it mean semi-permanent, because this was added maybe by Gulin, and I have to ask her what does she mean with semi-permanent, but I think she has a good reason, of course. Support the responsible development of lunar and near-Earth asteroid resources, developing space production of fuel and K resources, including the use of lunar, asteroid, and orbital materials, and early. Okay, I'm just reading the titles, not the whole point, because it will be too long then. Accelerate orbital debris recovery and reuse. Support the development of 100% reusable space vehicles and other transformative access to space infrastructures. Produce food and oxygen in space. Advance space-based solar power. I lost my file, sorry. support the development of civilian space tourism and accommodation industries, support space-related art, and bring art into space. So there is also a short text, of course, to accompany the goals that it will be presented. This is the motion that we will propose tomorrow for the votation to the Congress for votation. And okay, so I think it reflects the discussion that we had, the important points that came to the light, like the proposal of a conversion of military industrial capacity towards civilian space development, and yeah, giving priority and investments to the life protection in space is a very key point, also advanced by the excellent speech given by Isaac Arthur, the 30th of June during the opening session. And yeah, I think we know what to do from now to 2031.
But we have to do it. Yes, yes.
Okay.
Action. Yes.
Adriano, is there a specific goal to promote space and spirituality, and also the idea of extending space philosophies? I mean, I think these are critical to the fundamental understanding of space, because we are completely blinded by the science and technologies.
Right. I agree 100%. And let me say that if you think that inside Space Renaissance some good idea comes up, it depends from the fact that we have a deep humanist philosophy in our DNA, in our root. So we always think about, before designing, we think about requirements, and we start from our humanist concept and philosophy. Yeah. I think, yes, this should be evidenced in our final resolution somehow. Yeah. And yes, we can think about that. And also, to mention the further development of the philosophical work. Yes.
Thank you very much.
I do also agree with you that we have to work on really good space philosophy. And in our space philosophy committee, we are working on this, also on humanistic ethical principles for humanistic ethics. And you are all invited to work with us. Thank you.
Very good.
Excellent. Okay. So maybe we can close.
Yeah, we can close.
And see you tomorrow, of course. And see you tomorrow at the same time. And I think we can finish maybe in 3 hours, the maximum.
Yeah, we try to finish.
At 5.
And I propose a drink, you know.
Okay.
It's all
Cheers.
Thank you, everybody. Thanks, everybody.
Good job, everybody.